Let's see. Awesome. Good morning. I was still looking for my colleague Lisa. If you've seen her, that would be great. Otherwise, I'm now alone on stage to say all the boring stuff until it gets really interesting in terms of content. I got a lot of questions about Wi-Fi and stuff. But before that, I'm Stefan. I had the pleasure to help bring this conference together. So if you miss coffee, food, drinks, whatever, that's my fault. So welcome to day 2, or welcome if this is your first day. Oh, I'm getting a call. Wrong one. The wrong call, not Lisa. Okay. That being said, welcome to SQA conference again. This is now the main venue for the next 3 days. We do have excursions. We do have the conference dinner that takes place somewhere else. We will inform you like directly before that. Essentially, the plan for today is we have scientific sessions in the morning, then we have lunch break. Well, obviously there is a coffee break or fika time in the morning as well. Then we have the poster sessions, which will happen downstairs. We'll bring out the poster walls there. You find a spot, place your poster there if today's your session. And then you attend it during the poster session time. There will be also workshops today. That will take place in different rooms throughout the building. One is 1 floor up in that direction. The other one is taking place downstairs next to the entry, and the last one is on this floor on that side. We will have people guide you there, so just in case. And we kindly ask you, if you signed up for the workshop, to please go there, as spaces are limited and kind of due to the registration, you're otherwise blocking someone else's spot. So that would be really great. Then I got the question about Wi-Fi. You can connect either to Iterome, that's the easy part if you're from a university or a college. The other option is to use Chalmers guest Wi-Fi, enter an email and confirm within 10 minutes, so you're not kicked out again. Those are the options to access Wi-Fi. Then the most important stuff, food and drink. There is a bar with coffee, soft drinks and stuff back on this floor. There is food and stuff in the meeting room on this floor that is connected to the exhibition area. But there is also one upstairs where there are more very interesting booths that you can check out during the time you're not attending a session. I think this is all you need to know for now from the organizatorical part. Besides, well, there is an excursion tonight, and you can check if you received an email, if you've been admitted to one of the like place restricted excursions, or you can check within the app if you see a you're in sign. All of these will leave at 6 before the building, in front of the building, but there will be some to-go dinner before that, so you don't need to leave hungry. Great. With that being said, I think it's enough stuff about the organizatorial part, because we're all here for the first keynote of the day. And that's why we have Aziza Al-Manakli, who freshly moved to New York. And I was really wondering, and I didn't ask that actually, but I'm really wondering, as a tourist who've been to New York, how can you actually do research there? Because you have so much to do. How can you actually lock yourself in a basement room and do research? So I'd rather be not very excellent there. Glad she is. And she will speak about entanglement distributions across networks. And with that being said, please welcome Aziza on stage.
Thank you. Okay, it's on. Great. Hi, everybody. Thank you, Stefan, for the organization and for the introduction. It's really an honor to be here as a keynote speaker. Today, I'm going to tell you about research that I did while I was a PhD student and then as a postdoc later at MIT in the Engineering Quantum Systems group led by Will Oliver. The goal of the work is to convince you that you can use waveguide QED, or waveguide quantum electrodynamics, to do quantum networking. And so this is a subfield of quantum optics, and I'm really excited about how we can use quantum optics. Well, first, how we can demonstrate quantum optics with superconducting qubits in new ways, but then how can we also use that to help advance quantum technologies. So first, I'm going to make the case for why our quantum computer architectures in the superconducting solid state platform, why do they need to be modular? So here is an example of just a very simple diagram of a flip chip style qubit chip on top and the interposer chip on the bottom. This will have your control lines, resonators, and all. And so this is typically how you make big quantum chips in the modern day, and you can fit maybe a couple hundred qubits on a chip like this. But why would you need quantum interconnects? You need to be able to expand the size of your quantum computer in order to actually realize the potential of quantum computation. And so if instead you have modules of chips that can help you with yield limitations, package size limitations, this is what Andreas laid out very thoughtfully yesterday. Okay, but now if you break up your computer into different modules, you're going to have a way to connect them, and that's with a quantum interconnect. And so there are several styles of quantum interconnects to this day in superconducting qubits. Here, these are neighbor-to-neighbor or peer-to-peer interconnects. You could also have another type of interconnect which connects qubits on the same chip. This could be useful for realizing non-local coupling for QLDPC codes. But you also might want another style of quantum interconnect between interposers. This is to realize distributed quantum error correction protocols and really expand the potential of what you can do with a quantum chip. But in this work, we are investigating new styles of quantum interconnects with all-to-all or potentially many-to-many module connectivity. And so now if you can connect all the modules together with all-to-all connectivity, it's still an open question. How much more potential does this give your quantum computer? But this work is concerned about realizing these all-to-all style quantum interconnects. So how can we do this? Well, today I'm going to talk about 3 experiments where we realize quantum interconnects using the physics of waveguide quantum electrodynamics. The first experiment is where we realize directional microwave photon emission. So taking a step back, quantum networks, they enable modular and extensible quantum computation, and the goal of a quantum interconnect is to distribute entanglement between computational nodes. So far, with superconducting qubits, there are 2 main styles of quantum interconnects. The first is coupling via resonators. So here in this scheme, we have 1 qubit on one side of a resonator and 1 qubit on the other. And you can transfer quantum information and also create an entangled state by swapping an excitation from 1 qubit into the resonator and then to the other qubit and vice versa. So this scheme is bidirectional because you can transfer information both ways. However, it's limited in node connectivity and in distance. And it's basically, if you want to increase the distance between these 2 qubits, that changes your free spectral range of your resonator. And as a result, the modes will be closer together, complicating the protocol. So the distance matters in those types of schemes. But alternatively, there's another type of scheme where you can use itinerant photons as quantum information carriers, where you have a qubit on one side and a qubit on the other. And this is now, instead of a resonator, it's a unidirectional waveguide. So it has to be 50 ohm terminated. And in order to realize this setup, you need to have a circulator in the middle so that you don't have reflections come back from the other qubit. And so these schemes, they're more versatile. You can imagine these qubits can be larger distances apart or more arbitrary distances apart. However, you usually have to enforce unidirectionality with a circulator, which is a macroscopic microwave component that introduces a lot of loss. And so we're proposing an interconnect that combines the best features of both of these schemes. We want bidirectional communication using itinerant photons. But first, I'll explain, I'll contrast cavity QED and waveguide QED. So typically we think of, in circuit QED, we have our version of cavity quantum electrodynamics, where you have an atom inside a cavity and is protected from loss by that cavity. And so the cavity is protecting your qubit from the open environment, from dissipation. And this is the dominant architecture that we all know for superconducting quantum information processing. But alternatively, waveguide QED couples qubits to the continuum of modes inside a waveguide. So we intentionally couple qubits to this open environment. And because they're connected to the open environment, we can use it to release, route, absorb quantum information. So we can use waveguide QED to build quantum interconnects by purposefully connecting the qubits to an open environment using the physics of open quantum systems. So our goal for this interconnect is to have all-to-all communication with itinerant photons. Now I'm showing you a waveguide that extends arbitrarily, and we aim to design these modules where we can emit photons in the direction that we choose, like this, between any pair that we choose. And so how can we realize this? We're using the platform of waveguide QED, where a qubit couples capacitively to a continuum of modes and inside a waveguide. So this is what it looks like in the model, but in real life on the chip, here's the qubit capacitor, and you just have a direct capacitance to the waveguide, so that if you do excite this qubit, almost 100% of the time, it will emit its photon into that waveguide. And so you can consider superconducting qubits as good quantum emitters because you can engineer that capacitance to be strong enough. However, just a qubit on the waveguide doesn't have this property of directionality or chirality. You're equally likely to emit a photon into the leftward propagating mode as the rightward propagating mode. So half of the time you send a photon to the left and half of the time you send it to the right. So how can we engineer a chiral or directional coupling to the waveguide instead? We instead have two emitters on the same waveguide, and we space them a careful distance apart, λ/4, reference to the frequency of the emission. And we take advantage of a quantum interference effect between their simultaneous emission. And so the physics of this module is based on an interference effect between these two emitters in the waveguide. Okay, how does it work? So I've told you about these two emitters, Q1 and Q2. They're resonant at frequency omega, and we put them into this entangled state here. Pay attention to this phase. This phase is important. So we couple both of the qubits to the waveguide at rate gamma, and we space them a careful distance apart at λ/4, where lambda is the wavelength at the frequency omega in the waveguide. So this qubit state is going to emit and is going to become a photon state. How do we figure out what the resulting photon state is? We have to track all the phases of the coherent pathways. So the first possibility is if qubit 1 emits a photon to the right. We denote this outcome with the ket 0, 1, where we have 0 photons to the left and 1 photon to the right. Then we have these two phases to keep in mind. The first is the qubit state phase. Because qubit 1 emitted the excitation, the phase in front of this state, we're referencing it to 0. There's also the qubit position phase, which comes from the location along the waveguide. So from this propagation phase here. Next, if we consider qubit 2's emission to the right as a possibility, now the qubit state phase is e to the I pi over 2 because qubit 2 emitted the photon and the phase in front of it is e to the I pi over 2. The qubit position phase now is e to the minus I pi over 2 minus for rightward propagation, and the pi over 2 maps to the λ/4 distance from the reference of x equals 0. And so these two possibilities, they constructively interfere. They have the same phase in front of them. Now, if we make the same considerations for the leftward emission possibilities, you'll see that there's a destructive interference effect between both the leftward outcomes. And as a result, these two kets, they destructively interfere, and we only have possible emission to the right. Okay, so this story that I told you, it's predicated on the assumption that qubit 1 and qubit 2 are independent emitters, which in reality they are not. There is a coherent coupling mediated by the waveguide between them of strength gamma over 2. And so to cancel that coupling, we introduce a tunable coupling element that gives it the opposite sign of coupling so that we can truly treat Q1 and Q2 as independent emitters, because if they're coupled, they're going to be swapping while they're emitting, and that corrupts the interference effect. Now, if we want to emit a photon to the left, all we have to do is change the phase of the initial entangled state so that we have e to the minus I pi over 2. Now the interference effects flip. We have destructive interference to the right and constructive interference to the left. So to emit a photon in the direction we want, we just have to prepare the entangled state with the correct relative phase. Okay, so far I've told you about the physics of this part, where we have two qubits equally coupled to the waveguide and a tunable coupling element in between them. However, it's difficult to prepare the entangled state with high fidelity because they're so strongly coupled to the waveguide. And so what we do is we introduce two other qubits, Q3 and Q4, called the data qubits. And to prepare them in an entangled state, we use a tunable coupler as well, and we perform two qubit gates to realize the correct entangled state. And we have to transfer that entangled state from the data qubits to the emitter qubits, as shown here. And so this is what the chip looks like. You can see we have the emitter qubits in orange, coupler qubits in blue, and data qubits in pink. The waveguide here is in purple, and we have control lines and readout lines as well. So to emit a photon, the protocol starts with introducing an excitation into the system. So first, we implement a pi pulse on one of the data qubits. Then we prepare an entangled state with the desired phase between the two qubits using a parametric square root I swap gate. Then we transfer that entangled state from the data qubits to the emitter qubits using parametric exchange interactions. And as a result, you'll have the waveguide interference as described before, and you'll end up with a photon emitted in the rightward direction with this particular entangled state shown here. I think this is dead. Okay. Here again, this is the protocol to emit the photons in the direction we choose. And to measure the emission direction, or to measure the result, we measure the voltage that comes out of either end of the waveguide. And so that voltage operator maps onto the A hat operator. And so we can visualize the photon wave packet in both directions by integrating that voltage over time. And so you can see the wave packet for the rightward photon is shown in orange, and you can see to the left there's very minimal emission, and you can see the opposite when we prepare the other entangled state. You can see leftward photon emission in blue. To visualize these photons, we have to do heterodyne photon measurements where you produce a photon state, this is psi photon, and you combine it with added noise when you use an amplifier in your chain. Then you do IQ demodulation, and you end up with a signal S that has an in-phase and quadrature component. And you can integrate that signal and map it onto your moments of A and A dagger, your raising and destroying operators. And something to keep in mind, though, is that if you prepare a Fock state, if you emit a photon in a Fock state, you'll have, on average, voltage is 0. You can see in the Q function here. But in reality, so to visualize the photon wave packet like I did on the last slide, we have to prepare the equal superposition state instead, so that there's some coherence with ground, so that your the phase of your photon is well defined. Because if you emit a photon, a Fock state, the phase is ill-defined and averages to 0 on the left. So to visualize the wave packet, we prepare a superposition state shown here. That's just a detail. But that was all for visualization, but we need to take those moments of A and A dagger. Here you can calculate them by taking statistics of the signal that comes out of the left and to the right. And you can take these moments and correlations and map them onto a density matrix. And you can see we produce a leftward and rightward Fock state with around 96% fidelity. And it's important to show that you truly have one photon. Okay, so that's the end of the first experiment where we demonstrate directional microphoton emission. The next is how can you use microwave photon emission in a specific direction to generate remote entanglement. So our vision is to take these modules. Here, this is a newer version of the module where we have put the qubits closer together to enhance the coupling and make the protocol faster. But to make a quantum network out of this, where each of these modules is coupled to its own quantum processing unit, and each of the modules also couples to the same waveguide. And we aim to send photons in the direction we choose between the modules we choose, shown here. You can put other modules in a transparency mode simply by detuning the emitter qubits so that they don't interact with the photon. But we don't just want to transfer photons. The goal is to generate remote entanglement between these modules, as that is the resource that we need in order to do distributed quantum computation and gate teleportation protocols. So the next experiment, we take these two updated modules and we put them in their own microwave packages, and we connect a 6-centimeter niobium titanium cable, though the distance between the modules does not matter. And that's a big pro of this sort of approach. This is what the setup looks like inside the fridge. We have a package on one side and a package on the other side of the cold finger. Each one hosts a module, and then there's the cable in between where photons propagate through back and forth. So first, what we have to do differently in this experiment is shape the photon. So the absorption process is the time reverse of the emission process. And if you use a time-symmetric wave packet, that simplifies your control scheme significantly. And so what we do is we can vary the coupling between the emitter and data qubits as a function of time according to these wave packets in our control scheme. So this is just a demonstration of how we can get a time-symmetric photon so that we can emit and absorb using the same or similar pulses. Okay, to start the absorption protocol, first we excite a data qubit on the module. This will sound like directional emission because it's the same for the moment. Then we'll do a parametric square root I swap gate, produce the entangled state that emits a photon to the right. Now we shape our parametric exchange interactions to send a shaped photon to the right, and at the same time, we play the same pulses on the absorber module. And as a result, at the end of the protocol, we should have the same entangled state that we started with on the other module, on the data qubits. So in reality, this is 6 pulses, each with a very careful set of parameters. So in the end, this was too much to optimize by hand. I tried it, I hated it. So what we did was we turned to reinforcement learning. And the way that our algorithm was implemented, we started with a physics-based calibration. Our seed pulses, this was the best I could do by hand. This is what the absorption pulse looks like in the envelope. And so next, we choose a next set of parameter candidates according to a Gaussian policy. We send those parameters or those pulses to the experiment where we run the absorption protocol and we collect a reward. So our reward is the population on the data qubits at the end of the protocol. And then we compute gradients, update the neural network, which gives us a next set of parameter candidates according to PPO optimization for anyone who's interested. So all of that is one epoch. So this is one cycle of the experiment. And we repeat this a couple thousand times to optimize the reward here. This was very helpful for keeping the experiment optimal and getting everything on track, as with all these qubits and control lines, everything would drift. So this was just very useful to me as a person measuring. Okay, now how do we characterize the performance of the experiment? We conduct a set of measurements. You can think of, in this experiment, we have, let's say, 6 different photon detectors. So you can detect a photon at any of the 4 data qubits, and you can also measure it at the output of the waveguide on the right and the left. So the first experiment we do is we put the absorber module in a transparency mode where we detune the emitters so that they do not interact with the photon. And we let the photon pass by and land on the detector on the right. And so you can see we have a shaped photon there. Then we absorb the photon. You can see that the photon wave packet is suppressed in the rightward detector, meaning that, okay, we caught some of it. Next, we run an experiment by measuring the population of the data qubits as we step the pulses in time. You can see they start in a roughly 50-50 entangled state. And then on the data qubits, we do a similar measurement where they start in the ground state and we pick up population there. So in the end, what we're able to absorb is around 63% of an excitation, and I'll explain more where our different error sources are coming from. But we also perform the same set of measurements to the left. You can see similar behavior and maximum absorbed population, which tells us we're hitting the same limit in both directions. Okay, now so I showed you the populations, but to characterize entanglement, you need to perform qubit state tomography. So this is the resulting density matrix of a photon launched in the leftward direction and in the rightward direction. So you can see what you end up with is a mixed state of an entangled state and a joint ground state. So either you caught the photon, the qubits are entangled, or you didn't catch the photon and you're in joint ground. So what are the sources of loss? Sometimes we lost the photon, so that's incoherent loss, meaning we don't know where it went. So, but you can approximate the photon loss as the main source of incoherent loss in this experiment of around 18% or minus 0.86 dB. You can measure the insertion loss between the packages along the cable. In reality, you know, this photon is going through not just the superconducting metal, but also wire bonds and package traces that are those package traces are copper. So, you know, minus 0.86 dB doesn't sound like a lot of loss, but to a photon it is. It's 18%. Okay, and we can also estimate the qubit decoherence contribution of around 7% and sideband loss, which is a side effect of the parametric exchange interactions that we use of a single percent. And sometimes the photon arrived at the wrong detector, so that's coherent loss. And this means the photon didn't go where we wanted, but we figured out where it went instead. That's directionality error, meaning we sent a photon to the left, but it ends up at the right, and that happens a single-digit % of the time. There's also missed absorption, meaning we send a photon to the right, and the absorber misses, and it lands on the rightward module. So that happens 3 to 6% of the time as well. So in the end, these are our Bell state fidelities and concurrences in this first time demonstration. And we can account for an error budget at around 33%. Okay, this is characterizing the directional emission and absorption processes, but I told you our real goal is to demonstrate remote entanglement. And so how do we do that? Here I'm showing you the population traces emitting a photon to the left. And if we stop the emission halfway through the pulse and we play the same emission pulse, the same absorption pulse, so stop the emission pulse, play the same absorption pulse, you can end up with a W state of this form where all 4 qubits are entangled and share 1 photon. So we perform this experiment and we characterize the 4-qubit density matrix, showing that we do indeed generate remote entanglement using this scheme in both directions. So these demonstrations show that we can build a modular quantum network using directional photon emission in 1 dimension, in 2 dimensions, and in 3 dimensions as well. So a future step that we're hoping to do is gate teleportation, where now if you generate an entangled resource state, you can implement remote gates between qubits on different modules. And that's very helpful for distributed quantum computing. You can do a teleported C-NOT gate or a teleported C-unitary gate. And a future step that we're working on right now is multi-chip modules, where you have the interposer holding different modules on different qubit chips shown here. And our goal is to send photons back and forth between them with higher efficiency because they don't have to go through packages and loss. So that is what my colleagues are continuing at MIT. Okay, so that's the end of the first 2 experiments, which were about directional microwave photon emission and using that to generate remote entanglement. A more recent experiment is where we use waveguide QED to generate entanglement in a different way, in a scheme known as driven dissipative entanglement generation. And we use giant atoms to do that. So far, I did tell you about the different schemes for quantum interconnects, but I'm going to show you them on a different angle, where now that resonator scheme is a way to use coherent interactions in a closed quantum system to swap an excitation from one qubit to the other. And usually to implement these schemes, we need to be able to turn on and off this coupling, G of T, in a precise way. And similarly, for the photon emission and absorption schemes, you need to use both coherent and dissipative interactions, so G of T and gamma, to send information from one side to the other. But like you saw, it's very important the pulses and the calibration that you use to generate that entanglement. So there's an alternative proposal where you can use dissipative interactions entirely and a continuous tone to drive qubits into an entangled state instead. And this would alleviate the overhead that comes with tuning up these sorts of protocols, because all you need to do is turn on a steady state drive. And so remote entanglement generation usually requires precise calibration of interactions. Alternatively, we want to use the physics of open quantum systems to generate steady state entanglement, and this is what this later study investigates. So to date, there have been some demonstrations of driven dissipative entanglement schemes. Some of them, they use cavities, and these schemes, they require the cooperation of lots of tones, for example. There's also schemes based on waveguide-based dissipation, and these schemes are limited by that same coupling that you use to generate the entanglement. So that dissipation, that's your entanglement resource generator, that limits you in the end, because in the end your qubits are lossy. So how can you preserve an entangled state in the face of loss? So this is the paradox. Driven dissipative entanglement schemes are plagued by dissipation, and it's difficult to store useful entanglement that way. So how do we propose to get around this paradox? We use giant atoms. So typically, we have to consider atoms as small, meaning they're small in physical size compared to the wavelength of light that they couple to. And this allows us to take the dipole approximation in quantum optics, where we can treat the atom as a point-like object, and the atom couples to a single location along this waveguide. So here, yes, we have an atom coupled to a waveguide. A giant atom, on the other hand, is large in size compared to the wavelength of light that it couples to. So we can no longer take that dipole approximation, and we have to consider the different coupling points along the same wave. And as a result, there are interference effects between those different coupling points. that we can take advantage of. So we can exploit that interference given the phase difference between those coupling points. So in this experiment, we create a system of sequential giant atoms where each giant atom couples twice to the same waveguide with a particular phase in between these coupling points. And so how do we choose these phases? The first phase, phi, is the phase within an atom. So this is determined by the frequency of propagation and of the atom and the distance between the two coupling points and the speed of light. So the first frequency we're going to consider is if we set the qubit to omega sub, where now we have phi is an odd multiple of pi, we have a destructive interference effect. You can see both of the coupling points, they couple to opposite phases of the wave, and as a result, the atom decouples from the waveguide, or it's protected. So this effect is what I call individual subradiance. Instead, if we tune the qubit to omega super, or this is the super radiant frequency, such that this phi is now a multiple of 2 pi, you have constructive interference between the two coupling points. So now you have enhanced coupling that's controllable through the waveguide, and this is an effect that I call individual superradiance. Okay, now if we look at theta, or the phase between atoms, this is defined by the distance between the adjacent coupling points. You can see that the superradiant frequency, the same one from before, produces a constructive interference effect and a destructive interference effect, meaning that you get collective superradiance and subradiance. And as a result, you have the emergence of dark protected states and bright controllable states. So let me explain more. How does this interference effect work? So if we consider this qubit state, psi minus, imagine we have a way of putting the qubits into the psi minus Bell state. The state phase defined by the phase between the qubits is pi, and the waveguide phase, in this case, we set it to pi. This is well defined here, and you have constructive interference between these two phases, and as a result, this is the superradiant or the bright state, meaning the waveguide couples to this entangled state. However, if you instead place the qubits in the psi plus Bell state, you can see now the state phase is 2 pi and the waveguide phase is pi, and you have destructive interference between these two possible phase, or between the two phases, and this results in a subradiant state. And intuitively, you can see that, okay, if the qubits, they both have a positive amplitude, but you can see this particular frequency requires them to have opposite amplitudes. This state will not couple to the waveguide. So that's how you have a protected dark state. Okay, so our goal in this experiment is to prepare those qubits in that dark state and protect it from loss. So this is the energy level diagram of the system, where the qubits, they start in the joint ground state and you drive them through the waveguide. And here we have the superradiant and the subradiant state. So you can drive the superradiant state directly, but you have no access to the subradiant state, which is protected. So to open that interaction, we introduce a weak coupling, or a weak detuning between the two qubits, delta, which effectively couples the psi plus and the psi minus state. To give you a more intuitive picture, I like to think about the 2-qubit block sphere, where we have a way of getting to the psi minus state, and a little detuning on the equator allows us to slowly reach the psi plus state. And so this experiment depends on the interplay between 3 parameters: the detuning between the qubits, delta, the drive strength, capital omega, and the dissipation, gamma. So in this experiment, these are our parameters. We have really strong dissipation and very weak detuning. So our goal is to maximize the steady state population of the psi plus state. The thing is, even if you populate the psi plus state, you still can't use it as an entanglement resource, because to characterize it or to use it, you have to rotate the entangled state to do any algorithm. And so these approaches are still limited, and that's where the giant atom comes in handy. So I'll explain more. But this is the device that we use. We have two giant atoms coupled to the same waveguide, and we choose to have these spacings between the coupling points of 2 lambda super on the individual couplings and lambda super over 2 for the adjacent couplings. And it's also important to keep in mind that we also have the subradiant frequency to keep in mind. So we've designed the chip so that we have three halves of lambda sub on the individual. And this is important, I'll explain. So here I'm showing you the spectrum, the dissipation spectrum. So we sweep the qubit frequency from around 4.5 gigahertz to 6.5 gigahertz, and we measure the dissipation or the coupling to the waveguide as a function of qubit frequency. And you can see we have the two important frequencies. So we have omega super at around 6.2 gigahertz, and we have omega sub around 4.65 gigahertz, and that's where the atoms destructively interfere, and we can protect the atoms from dissipation there. So we'll drive the qubits into their entangled state at the superradiant frequency, then we'll flux tune them down to the subradiant frequency so we can protect and read out their entanglement. Here we're characterizing the collective superradiance, so you can see the qubits there parked around the superradiant frequency of 6.2 gigahertz, and we sweep one qubit through the other in frequency. You can see that when they're off resonant, you have a coupling of 4 gamma. When they're on resonant, that coupling feature broadens to 8 gamma, and that's a sign of collective superradiance. And you can detune the two emitters shown here in order to implement the protocol. So that detuning parameter is important and will drive the qubits at that center frequency. So this is what the protocol looks like. We drive the qubits through the waveguide for a period of time tau. This is considered a continuous drive. The qubits start at the omega super frequency where they're very strongly coupled to the waveguide. Then we flux tune them to the subradiant frequency with Z pulses, where we can perform X, Y, and readout operations to characterize the resulting qubit state tomography. So we're able to generate an entangled state of around 89% Bell state fidelity, where we can, we've done a lot of work with this work was done in collaboration with Anton First-Clacom's group at Chalmers right here, with some very powerful theorists that helped figure out every little detail of this density matrix. So you should read the supplement of the paper. It's quite enlightening. But the main limitation is the drive limit, and I'll explain more. Basically, the presence of the transmon F state limits the amount of drive strength you have without leaking to the higher manifold. And then there's also some decoherence. Okay, so here, this is another measurement where we measure the Bell state fidelity as a function of drive strength. And you can see there's a local maximum. Before this maximum, you're not driving hard enough to reach the full Bell state. After this maximum, you're driving too hard where you start to leak to the F state. And so next we'll show that truly this is a scheme that's after a certain transient is independent of time. So this is why it's called entanglement stabilization. We can drive using that continuous tone for an arbitrary amount of time, which significantly reduces the amount of overhead and calibration. And so here are the different rise times associated with the different drive strengths here. Okay, so our goal is to use this driven dissipation to create an all-to-all quantum architecture using giant atoms. So, for example, by choosing the particular frequencies of the qubits, we can determine which pair gets entangled with the same drive. So future work will show that we can generate simultaneous Bell states with this sort of scheme. You should check out our manuscript, which is now on the archive. And thank you again for having me, and I'm excited to take any questions you might have. First, I'd like to thank my team at MIT and MIT Lincoln Lab, without whom this work wouldn't have been possible. And I'm also plugging, I'm starting as faculty next week at NYU, and I hired 2 enthusiastic PhD students, and we're building the lab. So if you're interested, come talk to me. But thank you very much.
What a great talk, I think. Awesome. Like, I could literally listen for hours more, but unfortunately, evening keynote has an end. Are there any questions from the audience? And before we get those, I need to get the second mic, which I forgot. Any questions from the audience? Yeah, back there. I forgot to ask some. Well, sorry, it's closer, but maybe you can come to the front. We'll have someone helping with the mic later. I just forgot to ask that person for now.
So for our first experiments, you see that photon loss is quite important to limit your fidelity. Is it possible to detect this loss and post-select on it to make
And
your
post-select?
fidelity?
Yeah, I could have. I could have shown you density matrices that were post-selected, but in the end I said, okay, this is the result, and we want this to be a deterministic protocol, and it really has the potential to be.
Okay.
So it would have been like, okay, you get a 20% boost if you don't have photon losses. Yeah. But in the end, we're going to do these flip chip architectures, which hopefully won't have that same photon loss.
Thank you.
Thank you for this great talk. My question would be, if you manage to eventually get to 90-something% in your entanglement scheme, how do you plan on making these logical gates fault tolerant? Because even if you have like pretty high fidelities, right? If you have corrected qubits, you also need some kind of corrected interaction between them.
Right. Yes. So this is an active area of research, but I do think there's some theoretical work that has come out recently that shows that you're more resilient to losses in the channel, the quantum channel between logical qubits, than by about an order of magnitude. So I'm hoping that if you can beat 1.9, that might be good enough. If you already have error-corrected logical qubits, that will inherently help you in the channel as well. So if your error rate on your logical qubits is around 1%, maybe you can tolerate more in the channel. Ideally, we'd want it to be perfect, but it's an ongoing area of research.
Okay, thank you.
Thank you for the very nice talk. I have a question on the flying qubit approach, and I saw that you are limited by losses in the link mainly. So have you considered a eigenmode swap approach with like some virtual Raman kind of protocol that doesn't excite the link? I know that has got an FSR to deal with, but considering that 1 meter of RF coax cable has got an FSR of 100 megahertz and a quality factor between modes that is around 1e⁻⁷ typically, that might not be difficult to implement that link in centimeter or up to half a meter paradigm.
Yeah, that's a great question. There are schemes like with that resonator style interconnect where you can use a Raman style transition and not populate the waveguide directly, and that's a strength of those schemes. But then in the end, you have to consider the distance between the two and the length of that resonator, and so that limits the protocol. And then you won't be able to have all-to-all connectivity and things like that.
Okay.
Awesome. There is no more question for now. I think there is a lot of time to ask Aziza during any coffee break or fika time, during lunch, during the dinner, and throughout the conference. Please use this to chat with each other. I would like to thank the speaker once again just for also answering all these questions, and hope you continue this great work, even though you have a lot of great restaurants around you and a lot of great things to do, and I'm still impressed in how to do that. So thank you very much, and thank you for coming to Gothenburg.
Thank you, thank you.
So the next session will be chaired by my dear friend Mikko Möttinen, who is already here. Before that, I need to give you some information because Asisa, who's special in a way that she got way more time than everyone else, sorry for that. For now, in the first talk of the session, typically if this is an invited talk, has 20 minutes including questions. The other talks have 12 minutes including questions. I'll give you a signal holding up a piece of paper, that's how professional we are, showing you 2 minutes, and when it's over, like 0. So in that case, please finish your sentence. Otherwise, if you finish early, there is more time for questions. I hope that's all clear. We'll put up your presentation already for you, so you should just be able to click continue and go. And I hand now over to you, Mikko, and you can announce the first speaker.
Great, thanks, Stefan, and great to see so many people here. Now we are in one of the most exciting, or maybe the most talked about session, because it's about quantum advantage, methods, even experiments on quantum advantage. And personally, I think that quantum advantage, when we talk about it, we should always think about it with respect to the classical way of solving. Because fundamentally, quantum computers calculate in a different way than classical computers. And then there is no way to get around it. So please keep that in mind. And when you ask questions, maybe this will pop up. However, now it's my great pleasure to introduce you David Karpak, who is from QMIL and talking about towards quantum advantage with IQP circuits. So take it away, David.
All right, thank you, Mikko, and I can maybe take this second to thank the organizers again for putting together a lovely conference. Okay, yeah, I could maybe say take a second and say something about the company QMIL. So we are a quantum algorithms and software startup located in Helsinki, Finland. So we are interested in realizing quantum advantage on near-term devices or current devices and doing something practically useful with them, right? And this talk is going to be about that. Okay, so this is a collaboration with a bunch of the folks at QMIL. We have a quantum advantage team working on these types of problems, and they've all contributed very much. So even though I'm the one presenting, a lot of the credit should go to them. Okay, yeah. All right, so what I really want to talk about is quantum advantage with classical verifiability. So in the abstract, what I want to do, I want to run an algorithm on a quantum computer that can't be run on a classical computer, but then I want some mechanism for verifying that the result was correct, right? I don't own a quantum computer, so I have to do this with my laptop. So in theory, one could do this with Shor's algorithm. I just write a circuit that runs Shor's algorithm for some very large integer that I can't factor classically. I send it to a quantum computer. It sends me back the factorization, and I say, okay, this only took you an hour, so you must have a quantum computer because nobody knows how to do this classically. Right? So I would like, but I can't run Shor's algorithm yet. I don't think anyone can. So I need some kind of simpler way to do this, and I would like to kind of formalize this whole scheme in an Alice and Bob language. So I'm from kind of information security, cryptography, this area. So I like to think in terms of games involving Alice and Bob, right? So what I want to do, I want to set up a situation in which Alice constructs a test that only a quantum computer can pass. This test is going to take the form of a quantum circuit. She's going to also construct an answer key, a verification algorithm. And she does all this classically. So she can construct the test and she can grade the answers, and she can do that classically without too much effort. She sends the test to Bob, but she keeps the answer key locked in her drawer. Bob takes the test and sends back samples that he purports to have generated using a quantum computer. So measurements of the circuit with, say, input state 0. Sends back a bunch of answers to the test, and the verification algorithm grades Bob's answers and either gives him a pass or a fail. Right? So this is the whole setup. So Alice's operations all happen classically, and let's say in a reasonable amount of time, ideally polynomial in the number of qubits, but don't worry too much about that. And Bob should be able to run this on some kind of like near-term device, right? I don't want him to have to use Shor's algorithm for this. Okay, so sort of a promising candidate for this setup are something called IQP circuits. So I would like to realize the abstraction of the previous slide with a concrete family of circuits, and what I'm proposing is that we use something called IQP circuits for that. So an IQP circuit works like the following. So I take my initial state, all zeros, I hit it with n Hadamard gates, one on each qubit. It puts me into a uniform superposition. I apply some classical function to adjust the phase of each computational basis state. So this is just some diagonal unitary, right? And then I hit it with another layer of Hadamards, and what pops out, very interestingly, is the Fourier transform of the function in the middle, right? So the coefficient of each computational basis state is now the Fourier transform of my function evaluated at that state. So what this circuit does, if you plug in the zero state and start taking samples, it will sample each bit string, each computational basis state, with probability proportional to its Fourier transform. So already you should think that the quantum computer is doing something very interesting here. Computing Fourier transforms is incredibly hard, classically. It's, even for like a very restricted class of functions, it's sharp P hard. Sharp P hard, if you're not familiar with that, it means it's even harder than NP hard. It's like an NP hard problem, but you have to count how many solutions it has, not just find a single solution. Okay, so these circuits first appeared in the context of quantum computing in works by Shepard and Bremner. But I think kind of the formalism that I've written on this slide has essentially been there since like Gauss, since the discrete Fourier transform existed. Okay, so how can I take my IQP circuits and glue them to the formalism of the slide from 2 slides ago, and sort of construct some kind of mechanism by which Alice can verify Bob's quantum computation classically? So what I need to do is I need to get Alice to construct a pair, so a function and a trapdoor. So this is some sort of cryptographic game now, such that computing this Fourier transform is hard without the trapdoor. She keeps the trapdoor secret. That's the verification algorithm, right? So Bob can't compute Fourier values easily. He has to rely on his quantum computer to do it, right? But Alice can verify easily, so she has the trapdoor. So when Bob takes his samples, he sends back a bunch of bit strings. Alice computes these Fourier values quite easily with the trapdoor. And if she can compute all these probabilities, then she can run some kind of linear cross-entropy benchmark and verify that the computation was genuinely quantum. Right? So the first one just says that, like, the first condition here says that Bob needs to use a quantum computer to do this, right? The second one says that Alice can verify classically, reasonably efficiently. And the third condition just says that Bob can't cheat on the test, right? So, so the whole game is like, how do you plant a trapdoor in a function, right? So if I take a function and if I just give you a random function and make you run this scheme, of course you'll basically just be sampling a random circuit, and then verifying will basically be as hard as sampling classically, which kind of breaks the whole thing, right? If I try to run this game with random circuits, then of course it doesn't work because Alice has no way to verify. That's any easier than just sampling the circuit classically, which we're claiming that nobody can do, right? So okay, so I would love to dig into the details, but we work for a private company and we haven't exactly released the nuts and bolts yet. So I'll have to pass on describing the inner workings of it, but we will have a research paper coming out soon with the details of how you construct these functions with trapdoors that let you compute Fourier values quickly. Okay, so maybe I could transition now to talking about how do you actually run these IQP circuits on actual devices, right? So you have to take your function and somehow rewrite it in this kind of strange looking form, this exponential of a sum of XORs. This is sort of like kind of rewriting your circuit as an exponential of some Hamiltonian, right? If you want to think that way. And so you can take the whole circuit and phrase it all in terms of a binary matrix and a vector of angles, and then your circuit asks you to implement this matrix kind of column by column. So you take a column, you do C naughts until you're just left with C naughts, or like row operations, until you're just left with a single one in that column. You do an RZ according to the angle in that position, and then you do C naughts back. Right? So it's a very simple family of circuits. It's not. This is another reason why I think this is promising, is because like we know how to do a lot of these operations efficiently on actual computers. Right? So this column by column method, it's sort of, if you just think about it for a second, it's clear that it works, but it's a bit too naive. It'll get you way more C naughts than you need. So we have developed like much better methods for constructing such circuits, which basically you just choose the C naughts incredibly cleverly, and a bunch of them cancel, and you're left with a much shorter circuit that implements the same unitary that defines F. We can also do some kind of trade-off between like C naught count and depth for these circuits. So I can do more C naughts at a time. That gets you a shallower circuit. You're going to do, so you can trade off, you can do more parallelism, so you get a shorter circuit, but more C naughts. And then we can also kind of tailor them for like limited topology, right? Okay, so what do the actual numbers look like? If I go and try to build these circuits, what are the important metrics here? So I think there's basically two. If I'm interested in running this on like a near-term device, the C naught count and the depth, right, of the circuit. We have the number of qubits here on the x-axis and the C naught count on the y-axis. And the bigger this matrix is, the more columns it has, the harder it is to simulate classically. So you should think that like the green curve, maybe you can simulate it classically with some hardcore like ZX calculus methods or whatever, but the orange curve is even harder and the blue curve is even harder than that, right? You can also think that the number of, it's just more like about the number of T gates really, right? So the blue curve has the most T gates, so you should think it's the hardest to simulate classically. So where do we expect these problems to be hard, this Fourier sampling to be hard for classical? Is something around 50 qubits, like where you expect random circuit sampling to be hard for classical. So past like 50, we get sort of an advantage regime that I've bubbled here. And so the numbers are not too bad. Like we expect this to work with a few thousand C naughts, and then in the depth, if I greedily construct the circuit to always pick the best C naught every time, then the depth of the circuit is in a few hundreds. So like these are not terrible numbers. Like this is not like Shor's algorithm numbers here, of course. If I try to do more C naughts at once, I get a few more C naughts, but I decrease the depth of the circuit. So like here, this is probably more appealing. There are some ion trap devices that let you do essentially 8 C naughts in parallel. And so that's why I set the parallelism equal to 8 here. So you get a few more C naughts, but the depth of your circuit is way shorter, so you have less to worry about with respect to like coherence time. So we've run these circuits on ion trap devices. You can see we get positive cross entropy all the way up to 72 qubits. For the circuits we ran on this experiment, we found out after the fact that we could actually, with great effort, extract the trapdoor classically. But that's sort of the only problem, right? The problem is not that you can't simulate these using like an MPS simulator. You can't simulate them by trying to classically run some like fast Fourier transform. You can't do any of that. The only thing you can do is try to find the trapdoor. There's nothing else you can do. The point remains that like we can run these circuits and get like positive XEB results for something like 2,500 C naughts. So we are very, very close to the regime of being able to run these on existing devices. Of course, this is not the ion trap qubit in algorithms conference. This is the Superconducting Qubits in algorithm conference. So if I try to put these circuits on a grid, if I don't allow myself to do arbitrary CNOTs, but only ones between neighboring qubits, I get this picture here. So the CNOT count, of course, goes up, but it's still not crazy. Like in the advantage regime, you would expect to achieve some kind of quantum advantage with, let's say, 8,000 CNOTs. I'm allowing myself to do any allowed I'm maximizing the parallelism because, of course, on superconducting devices, you can do as many CNOTs as you can at a time. Right? The depth is let's say, I would say comfortably less than 2,000. Right. So this is, I think, where we're heading next experimentally. And of course, there's more I would like to say about how to actually put the trapdoor into the function and why we think it's classically hard to extract it, so that the adversary, basically Bob, must have a quantum computer if it returns us samples that passes the XEB test. And I would like to say more about how to actually build the circuits, how to minimize the CNOT count and depth, because I think we can do this better than anyone else can. But yes, this will have to wait for a research paper that I hope will come out very soon. So with that, I will end my presentation.
All right, thanks, David. So, time for questions, please. Who has the... Yep, over there.
Great, thanks for the talk. I had a question about, you mentioned briefly that you think they're not suitable to be simulated with MPS states or similar methods. Could you say a few words why you think that's hard? Because I think
Sure.
my tensor network friends always tells me that they are very good at it. So
I mean, they are very good at it, but they start collapsing when these simulation methods always start collapsing when like one of two things happens. Either there's lots of entanglement or there's lots of T-gates. And we have both of those properties, right? So like if you can just if you forget everything else about the circuit, you can just remember that I'm specifying it by a giant number of qubits by some number m matrix, right? M is, let's say, a small multiple of n, like 4 or 5 times n. So let's say 50 by 200 matrix, right? And the columns are going to be arbitrary. Every column induces entanglement between two of the qubits where there's a 1. So there's an enormous amount of entanglement. And also every column gives you a T-gate. So there's something like 200 T-gates and a whole bunch of entanglement. And I think, as far as we know, that these MPS simulators, they just fall on their face once the number of columns is past like 50. Oh.
Great, thanks. Some more questions.
Yes, so the question is, what would be the minimal phase which you have to control? Say pi divided by 2 to power 50, or
No,
no,
just T-gates. Just, you only need T-gates. You only need CNOTs and T-gates. You don't need phases smaller than pi over, I can never remember the normalization if it's pi over 8 or pi over 4, but you don't need pi over 2 to the n or whatever that you would need for like an arbitrary QFT.
Okay.
All right.
So how do errors propagated your scheme? You know, random circuit sampling sort of has this background that is kind of nice. How does your scheme deal with errors? And how do they accumulate?
I didn't address that question at all. So I mean, ultimately, all I want to do is just pass an XEB test, right? I just want the samples to, so if there are some errors but not too many and I pass the test, then I don't really care what happens otherwise, right? But I will say, like, you have to, if you sort of think about implementing the matrix, implementing the circuit, in other words, matrix like column by column, if you make an error in the first column, then you've lost. There are sort of kind of like natural algebraic error, I guess, detection mechanisms you can put in by adding basically more rows to the matrix and using some classical error correcting theory. This won't help you correct the errors while the circuit is running on the quantum computer, but it will at least will let you filter out some noise.
All right, let's thank David and move to the next speaker. All right. So the next speaker is Yuval Baum from Q Control, and he's talking about evidence for runtime quantum advantage in simulating large-scale fermionic models on a digital superconducting quantum processor. So, or
no, it's not
the
this
slide
one.
says that it's Lakshmi Sankar.
He'll find it in a second.
But it's Yuval who is giving the talk. Okay.
I can improvise with the other talk as well, but I'll prefer mine. All right, that's the right one. Okay, hey everyone. So I'm going to tell you today about simulating fermionic systems using quantum computers, and you can read it all in this manuscript. Maybe just one word around quantum advantage, because this is a common theme here. All right, so I'm going to focus on quantum advantage of the second flavor, the ones that are more focused on problems that people care about independently of quantum computers and not problems that are designed in order to benchmark quantum computers. It's a bit cut here, but never mind. The advantage of these kind of quantum applications is that people care about them and spend decades in developing very performant classical tools to solve them, so we can compare to them and understand where we're standing compared to the best classical tools out there. So what I'm going to show you today is a simulation of fermions on the lattice, the Fermi-Hubbard model, up to 60 sites. We are doing that on IBM quantum computers using up to 120 qubits. And I'm going to show you two different investigations. The first one is more physics-based, showing you the hallmark of fermions in 1D spin charge separation, but then also doing quite thorough benchmarking against many different classical methods. So in a nutshell, what is the problem that we are trying to solve? Dynamics. I give you Hamiltonian, I give you initial state, I give you a set of observables that can be quite large. Then I'm asking you to just find what you cannot see there actually, the time evolution of all these observables. And here you can see the Hamiltonian that we have is just a Fermi-Hubbard model for those of you who are not familiar. It's just fermions on the lattice with hopping term, interaction term, and on-site terms. You can see that in this case, all the coefficients are constant, but they don't have to be. Actually, don't believe me. We put this tool available for now only on IBM devices, but in this tool, you can actually set these parameters to be site-dependent, time-dependent, whatever you want. Then we need to choose initial state. So we typically choose a very simple initial state, but that's also not something that we are restricted to. We choose typically these Fock states that have filling. So for example, the antiferromagnetic state where each site has a single electron with alternating speeds. All right, so one slide of details before I move on. Unlike spin models, it's quite hard to use quantum computers for fermionic models because they don't map naturally to quantum computers. You need to go through the Jordan-Wigner transformation, which means that now things are a bit more complicated. Even though the underlying lattice that we are using is 1D, you actually cannot encode it to quantum computers without swap. Definitely not on 1D, even not on a square lattice. Because first of all, each fermionic site now is represented by 2 qubits that represent the 2 spins. And just for example, taking the simple hopping term and writing it in terms of X, Y, and Z gives you these 2 qubit terms, but also these 4 qubit terms. So that's why you need quite a lot of conductivity, and running on superconducting devices, part of the challenge is how to compile and embed these models to this limited conductivity, and then how to construct these series of trotter steps to make sure that your error is not accelerating. So big part of the paper, we focus on how do we embed and compile these things, and how do we save about 2x on the number of 2 qubit gates. But even with these very efficient embeddings, we still end up with quite large circuits. So it's a bit hard to see, but the biggest circuit that we are running has almost 14,000 2 qubit gates. So these are quite big circuits. So we had to implement quite a lot of active error suppression in order to get very high accuracy from these circuits. And I'm emphasizing error suppression and not mitigation, because the other things that we care about is speed. The overall QPU time that we have is of the order of 2 minutes, and the wall clock time, including everything, is around 4 minutes. So exponentially overhead mitigation is out of the question here. We cannot spend tens of hours to do post-processing and run different mitigations. So everything that I'm showing you here is just plain running on the quantum computers, just using heavy error suppression in the back. All right. So what do we see? So first, a bit of physics. So one of the hallmarks of fermions in 1D is spin separation. Spin and charge propagate in different velocities. A way to probe that is to introduce a vacancy, a defect in the middle of the chain, and then just follow spin and charge correlations, which again, you cannot see here, but that's what we are following. We just want to see how spin and charge correlations spread in the system. So this is space, this is time, this is data from the quantum computer, and we are following correlation, both spin and charge correlations. These are two-body observables that we are following, and you can extract these velocities from this plot. We are running that for different interactions, and we can because each experiment is 4 minutes, so 10 experiments with different interactions takes under an hour. And we can compare it first to analytics, both in the low interaction regime, we can solve it, and also in the large interaction regime where we can use analytics on the beta ansatz, for those of you who are familiar. But the nice thing is that even in the middle regime between them, which again, unfortunately, you cannot see, we can compare with numerics because that's the only thing that's available in these regimes, and we get very good quantitative agreement, not just qualitative agreement. But now the fair question is, how do we compare to classical methods? Because as I said, people in computational physics and condensed matter spent decades in developing very performant classical methods to solve these problems. So in the paper, we are comparing to 7 different classical benchmarks. Don't worry, I'm not going to tell you about all of them. I'll focus on one, TDVP. It's a very popular method, and we are using open source libraries like iTensor, for example, to simulate these. These are MPS-based methods. So even if you know nothing about MPS, the only thing that you need to remember is that there is a single parameter, bond dimension, that allows you to trade off between computational resources and accuracy. If this number is low, you run the simulation very fast, but not very accurately. If you crank it up, you gain accuracy, but it comes at a price of computational cost, memory, runtime, and so on. So of course we have 60 sites, 2 spins, it's a lot of data. So let's start by focusing on one. Let's take one site, one spin species, and follow its occupation evolution. So the markers is the data from the quantum computer, and the solid lines are different classical simulations with different bond dimensions. Now it's a bit hard to see, but up to around evolution time of 2, all the classical curves are on top of each other. But now let's zoom in on this rectangular, and this is what you can see here. Here you can see that slightly the classical curves start to separate from the pack, and they're doing that one by one according to the bond dimension. The first one is the lowest bond dimension, the second one is the second bond dimension, and so on. The only curve that can really keep up with the quantum data all the way to the end is the largest bond dimension. Now, of course, this is one site, one spin. We can average over all the 120 different spins and sites that we have and ask how far the classical method is from the quantum computation. And this is, now you don't see the most important part of the plot. So what you cannot see here is that here you can see the difference between the quantum computer and the classical computer, and the same thing again. They start to separate from the quantum data, and as we go to larger and larger bond dimension, you can keep up more and more. But even here, the largest bond dimension start to go up, and at that point, we don't really know whether it's because the classical start to lose accuracy or whether the quantum solver is starting to lose accuracy. Another interesting thing is that there is some noise floor, which we understand. We are doing trotter simulations, and also we have shot noise because we are estimating observables with finite number of shots. So we estimate this noise floor to be around 0.0%, and you can see that it's quite accurate. So whenever the classical methods seem to perform, they seem to be around this error from the quantum computer. So when we talk about runtime advantage, this is what we are talking about. So the quantum computer scales very favorably. First of all, it scales linearly with the depth of the circuit, the number of trotter steps we have, and it doesn't scale at all with the number of qubits. If we'll have twice as big devices, we could run exactly the same simulation with the same time. This is not the case for the quantum solvers. Here you can see that as you go up in bond dimension, the time scales exponentially. And overall, the difference in computation time has orders of magnitude difference. All right, so now you can ask, well, we just tested these methods. Can you do better? Can you use GPUs? Can you just push more? And the answer is that, well, apparently yes. And luckily, some others did that for us. So in the 3 months since we published this paper, 2 very prominent groups in the field, the Oros group in Spain and the Garnet-Chan group at Caltech, both tried to reproduce our papers using classical methods. They both use quite novel methodology that is not available in open sources, and both of them are using GPUs. They are using H200 NVIDIA machines. These are $50,000 machines, and they're not even using one, they're using many. So for example, in this paper, they use 4 of such big GPU machines. So there are 2 interesting things in this work. First of all, they certify our results, because what they're showing that even when they're using this insane bond dimension, 62,000, I don't know if someone here running these kind of simulations, but this is absolutely insane, they can see that the difference from the quantum computer is pretty much flat. That's the curve that you can see here, which means that all the results that we got, even the ones that we cannot certify because we cannot go big enough, are actually accurate. And the same thing happens also in the Chen paper, that they also certified all the 2-point correlation that we have in the paper. So that's first of all nice. But the other thing is that even with these GPUs and even with these very novel methods that they developed, they are still 36 times slower than the quantum computer. Now, of course, they celebrate that as an example that they can close the gap, but I think the overall statement is quite interesting. I remember that just a year ago, just having the ground state of a 10 by 10 matrix was considered as something great for quantum computers. And now we're at the point that the best numerical groups in the world use heavy GPU machines and very novel methods and celebrate being just 36 times slower than a quantum computer. So whether it's advantage or not, I'll leave you to judge, but clearly scaling is in our favor, and having 4 times better computers and twice bigger computers will eventually open a gap that no one will be able to close. So, thank you.
Great, thank you. All right, time for maybe a few quick questions. Anybody? No, I don't see. So maybe I'll just ask that in the papers of the others that you cited, I guess on the first one took down it to 36x. The second one with a supercomputer, I guess.
I mean, they're doing the calculation in about an hour, where the quantum computer is around 2 minutes, so it's give or take 30x.
Yeah, but I guess they didn't use the full sort of supercomputer. They just used like 1 GPU on that, right?
Correct.
Yeah, so if you use a supercomputer, you would still be faster, I guess.
Not everything is parallelizable to death, but
well,
yeah,
of course, it would need to be shown. Yeah,
well,
that's true.
If you have infinite resources, that's fine. By the way, you can also parallelize the quantum computer in general, right? I mean, we are running 30 Trotter steps, 20,000 shots per each because we're using 1 machine. But if I have now 20 different machines or a big machine, I can parallelize it by 20x or 30x as well.
All right. Okay, let's thank the speaker again. All right. And then we will move on to Maxime Dupont from Rigetti with the title of Navigating the Path to Quantum Utility in Optimization via Quantum Preconditioning. Thank you.
Hey. Hi, everyone. Thanks for the introduction. So I'm Maxime Dupont, and I'm a researcher at Rigetti, which is a quantum computing company developing superconducting hardware in California. And I'm going to talk about quantum algorithms, and in particular, quantum optimization. Okay, so when we say quantum optimization, what we mean is discrete optimization, and this is about solving problems which are defined over variables taking discrete values like 0 or 1. A very famous example of such a problem is a maximum cut problem. You have a graph made of vertices, edges, and the goal is to find a bipartition of that graph such that the number of edges between the 2 groups is maximized. And you label the vertices of the 2 groups by 0 or 1. How do we tackle this problem? We're going to write it as an Ising Hamiltonian for which the ground state is going to be the optimal solution of the problem. And so we have Ising spin configurations corresponding to bit strings. Each of them is a candidate solution, and the best solution is the ground state. So because we are looking to find the ground state of a Hamiltonian, a quantum phenomenon that comes to mind to do that is quantum adiabaticity. It's at the basis of quantum annealing, and the idea there is that, well, maybe quantum tunneling can help explore the solution space more efficiently. Another option we have are variational quantum circuits. There we have gates. Some of them are parameterized. And the goal is to find the value of these parameters such that the output of the quantum circuit does the job that we want. And here it's sampling bit string as close as possible to the ground state. And a very famous example and physically motivated in the context of optimization is the QAOA, and it's labeled by P, relating to its number of variational parameters. And then we have quantum algorithms targeting more fault-tolerant quantum hardware like Grover type search and the quantum Fourier transform. And in the following, when we talk about quantum algorithm, it's always going to be about the QAOA. Okay, so all of these algorithms, including the QAOA, the way it works, you run it, you get a bit string. That again, so that's a candidate solution to your problem. There is a world behind bit string, and in particular, we can do things with expectation values. And I want to make the case for a specific type of expectation value, which is a ZI-ZJ correlation. And obviously, it contains information about the problem and the solution because this tells you about the average orientation of your spins. And so when you do that on a problem, you get a matrix at the end, a quantum correlation matrix. So from that object, what I'm saying now is like, well, you have a matrix, you can diagonalize it, finding its leading eigenvector, and sign round this leading eigenvector. If you sign round it, you end up at the end going with a binary solution, which is what you want in your discrete optimization problem. So you do that, and then we can look at the normalized ground state energy versus the number of variables. We do that for random regular graph maximum cut problem based on the QAOA at p equal 1, and this is data that we get here. We can also look at like the performance of the standard QAOA directly from the bit string we sample, and we also plot that here. And we see there is a 30 times difference between the two. And what's interesting, and that's the point I want to make, is like the algorithm that is running under the hood is absolutely exactly the same. We're just doing something different with the data. To understand why it makes sense at all to do this thing, we can do the same strategy purely classically. So purely classically, we also have a matrix. This is this matrix W. It encodes the couplings between all the spins in the problem. And what we can do is take that matrix, diagonalize it, find the leading eigenvector, sign round it. And then what we get is exactly the same solution as the quantum version based on p equal 1. Exactly. And it's not a coincidence. It turns out we can show analytically that the classical and quantum at p equal 1 are equivalent. So this gives like why it would even make sense to do that on the quantum side. The way we show this is by showing that the quantum correlation matrix and this classical matrix encoding the couplings, they commute with one another, and so they share the same eigenvectors. So quantum classical at p equal 1, that's exactly the same. So why quantum at all? Well, there's another limit where we can say something. That's where p goes to infinity. And in that case, the leading eigenvector encodes the optimal solution of the problem trivially. And so what this says is like, well, already if you go to p equal 2, you can get an advantage with your quantum version over the classical equivalent. If we take a step back, what we have here is like, we have a problem, we can feed it to, that's what we call a relax and run solver. We get a solution, or we can take a detour, compute this quantum correlation matrix based on the QAOA, and feed that instead to the relax and run solver. Relax and run solver are very attractive analytically and mathematically because they are based on linear algebra and we can say something about the performance, but in practice, they are not the best solver for solving discrete optimization problems. And so why stop there, right? We can basically now think about like using any classical solver. And then I'm going to rebrand this like quantum correlation matrix by like quantum preconditioning, because what we do in the end is just transforming the input problem by the QAOA. And so I want to make the case for like this more general approach. Let's use instead simulated annealing. Simulated annealing is a state-of-the-art classical heuristics when it comes to optimization problem. It's based on Monte Carlo. We are still solving the same kind of problem as before, random regular graph max cut with about 4,000 variables. And here I'm plotting the normalized ground state energy versus the classical runtime. It's purely classical data, and so the longer you run your classical solver, well, the better you're doing. Then what we can do is like compute this quantum correlation matrix or precondition the problem. We do that based on the QA at p equal 1. That's the tilt curve here. We can do that based on the QA at p equal 2. That's the magenta curve here. It's a bit difficult to see what's going on. So one thing we can do is take a cut there and ask what is the runtime for the simulated annealing solver to get to a 99.9% performance. So that's what we have here. That's the runtime versus number of variables. We have about 4,000 variables, so that's the data points we have over there. And what we see is between, we converge to 99.9 about an order of magnitude faster when we do this quantum preconditioning step. So this is working. And then we can repeat the exact same procedure for different system sizes, and we observe the same trend. So, you know, what we do in the end here is like we make a detour to compute this quantum correlation matrix that we then feed to the classical solver. And so if we want to be fair in a benchmark against a purely classical approach, we should account for the time it takes us to compute this quantum correlation matrix. And a way to think about it is we can look at the time difference between classical and quantum there, and that's going to give us a time budget. If we manage to compute this quantum correlation matrix within that time budget, well, it's worth making the detour to then feed that correlation matrix to the classical solver because we'll be faster. If not, not worth it. So to feed, to fill this plot here, let me tell you a bit what we do. So we want to compute this quantum correlation matrix. It involves expectation values EIZJ. You may have noticed in the beginning, the sizes of problem we're considering, it's like in the thousands. And thousands variables means about 1,000 qubits. We cannot do naive simulation of 1,000 qubits. And so the way we're going about it is like we're using a trick, a light cone trick, where we use two things, properties of the structure of the QAOA circuit itself and properties of the problem we are considering, which are sparse. And instead of running one massive QAOA circuit on thousands of qubits or variables, instead what we can do is run one subcircuit per expectation value EIZJ we are interested in, and those are much, much, much smaller using this light cone approach. So we do that with state vector emulations, so purely classical emulations there at p equal 1, p equal 2, that's the runtime it takes to run those emulations versus number of variables. And what we see is that for the large enough problem sizes, well, we are within the budget. And so that's great because basically we have some quantum inspired advantage where like it makes sense for the to compute this quantum correlation matrix and then feed it to simulated annealing, and we get like a boost in terms of how fast we converge. How do we get a real quantum advantage? Well, we need to go to much larger circuits, which we cannot do classically. We need to make sure that the quantum computer is fast enough also to do that. And so we need to go to much larger p-values when it comes to the QAOA. So summary, I wanted to make the case for quantum optimization algorithm based on expectation value. Those are well suited for near-term experiments because they rely on expectation values, and those are like more amenable to error mitigation technique. It's also better suited or okay for superconducting hardware because of the high sampling rate when it comes to computing expectation values. Some next steps, I mean, it works pretty well. We understand why when it comes to a classical solver from which it's easy to derive something analytically. That's like the eigen decomposition approach. It's a bit harder when we are thinking about classical heuristics, but we have some ideas we want to explore. And then we want to look at other solvers and other type of RAM where like you have a hard constraints where basically some of the candidate solutions are just simply invalid. Want to highlight some of the works we did at Trigity over the last few years in quantum optimization. And with that, I thank you all.
All right, thank you. And now some questions.
Okay, maybe I understood it wrong, but your graph was random, right?
Sorry?
The graph was random, right?
Yes.
Okay, but then there were some plots where you were showing like distance to the ground state and number of sites was 200. But then how did you know this ground state?
Oh, because there are classical problems, we can brute force with classical solver, which are very good for solving that class of problem. We just run, and then we get.
This is 2 to power 200
Yeah,
possible bit strings. You
yeah,
cannot
but we can also solve these problems with heuristics. We don't have to enumerate all possible solutions. I mean, if we wanted to be like absolutely sure we have sampled the exact ground state, that's all we would likely need to do. But there are also very good and powerful heuristics where like you run it many times and with high probability it will find the ground state, and then you can have good confidence that it has found the ground state.
Right. Any more questions? If not, let's thank the speaker.
Thanks.
Thanks, Maxine. All right, and the next speaker is Philip Orman from Parity QC, and he's talking about demonstrating efficient quantum optimization with parity twine.
No problem. We don't see the screen anymore. Because otherwise it's cutting.
Okay. Oh, no problem. All right. Thank you. All right. So thank you for giving me the opportunity to present our latest work on quantum optimization, which we actually did together with IBM Quantum and Parity QC. So let me start with the very obvious observation that quantum optimization is hard. And what you see in these figures here is from a paper of the Google team a few years ago, where they tried to solve a couple of optimization problems with the QAOI on the hardware they had back then. And they were trying 3 different problems. One that would fit, okay, that doesn't work. One that would fit on the hardware graph, then a 3 regular problem, and an all-to-all connected problem, which is the SK model. And if you look at the figure on the right, you see that if they increase, so what they showed there is how close they get to the actual solution. So 1 would be they find the solution, and 0 would be they hit the random sampling baseline. And you can see the noiseless simulations look quite promising, but if they do their experiments on the hardware, especially for the problems that don't fit the hardware grid, you reach random sampling relatively fast. So this basically tells an important takeaway for quantum optimization. One major bottleneck is the routing of the problem to your QPU. Especially for superconducting qubits, your QPU topology is limited. So it's very important to find an efficient mapping of general optimization problems onto the hardware. And this is exactly what we are trying to solve with parity twine. So parity twine and the whole parity computing paradigm has the fundamental idea that you implement the relative alignment or the parity of multiple logical variables or qubits onto a single physical qubit. And this is then what we call a parity qubit. And these parities, these correlations, these pair correlations are created with native two-body gates in your hardware. And we can sort of track the information these parity qubits take by using our parity twine formalism. And to understand a little bit better how this works, I want to point you to our sort of core building block of the parity twine method, which is the double CNOT gate. So think about you have 2 qubits, L1 and L2. So these are, let's say, the set eigenvalues of these 2 qubits. And if you run the double CNOT gate, which is actually equivalent to a CNOT gate and a swap gate, you would sort of create the parity of 1 qubit, that's L1 times L2, and move the label from 1 qubit to the other. So you're kind of in one operation moving the information and creating parities. So if you're now stacking these double CNOTs along a chain, which we call the parity twine chain, you can see you can create all correlations which include qubit L1. Now, if you combine these parity twine chains to a network and you kind of follow the parity information with a parity flow formalism through the circuit, you can see you create actually all correlations which are possible in a very compact circuit with a lot of parallel gates. And this leads actually to a very efficient way of implementing the QAOA circuit and other circuits. And if you compare that to other values in the literature, we could actually see that we could outperform the best known solutions for all qubit topologies. So what you can see here is the average 2-qubit gate count versus the inverse connectivity of the QPU topologies. And you could see we could get down the 2-qubit gate count for all of them. And this is not limited to QAOA. I think it also applies to IQP circuits. Last year, I actually demonstrated that we could show some nice results for the QFT in this way. But now I want to show you a little bit how we use this for quantum optimization. And this is in our collaboration with IBM Quantum. And it's not just enough to have a very good and efficient way of implementing the quantum circuits. You actually, to make the best use out of the current noisy QPUs, it is very important that you basically do your best at every stage in the optimization pipeline. And that's why I want to very quickly walk you through the individual steps in our optimization pipeline. So we start with the optimization problem. For simplicity, you can think about it as a QUBO. And then the first step is actually the pre-processing of the problem. So before we go to the QPU, we are pre-processing the problem. And here we are using a very unique way of doing this. And this, I want to give credit to our collaborators from IBM Zurich, Daniel Egger and Stefan Wörner, who actually taught us this nice trick. So we start with doing a mean field AOA. So what is a mean field AOA? It's basically a very efficient way of classically simulating your QAOA. So what you do is you replace the quantum operators with a classical spin vector, and you assume that the density matrix of your system factorizes in the mean field approximation. And if you do that, you can actually run the whole quantum optimization on your classical computer quite efficiently, and you can see how the spin evolves in this nice figure. And depending on the amount of quantum correlation you actually need to solve the problem, the mean field AOA will already get you very close to the actual solution of your problem. And then we sort of take this state, which we get out of the mean field AOA, and go to start the QAOA from there, using the warm start QAOA idea. So what you do there is you do Y rotations at the very beginning of your quantum circuit, and the angle of this Y rotation is basically informed by the classical spin you get from the mean field AOA. So that's how we sort of pre-process the problem by already starting from a state which is kind of close to the solution efficiently. So that's important to do it efficiently. And then it comes to the core of our optimization pipeline, which is sort of this parity twine compilation. And here, since we wanted to tackle large systems, we said it's okay to restrict ourselves to depth 1 QAOA. And the advantage with that is you can train the QAOA angles classically efficiently on your classical computer. So you don't have to train the angles on the QPU. And in the heart of that is the parity twine compilation of the QAOA circuit. And you can see here a plot which shows the 2-qubit gates you need to implement one layer of QAOA for a 100 problem, for a 100 variable problem. And what we change here on the x-axis is the connectivity of the problem. So one would be an all-to-all connected problem, and then you sort of reduce the connectivity of your problem. And you can see that when you compare all the common compilers out there, like Qiskit, and you compare it with our parity twine compilation, we could actually improve on that for all problem densities you could have. And this is compiled to a square grid, as more and more hardware providers building square grids now. And there's actually a second y-axis, which kind of shows what, according to the roadmap of IBM, is considered feasible within which year. So you can see you could already run this year on an IBM Nighthawk device 1 layer of our compiled QAOA for a 100 node problem. All right, so after we have sort of optimized the circuits, we send them to the QPU, and then we will sort of post-process the data that comes from the QPU. And here we are just using a very simple greedy local optimizer, which just flips spins, and it will immediately accept the spin flip when the energy got down. And then it just, so this is also called zero temperature Monte Carlo, if this is more familiar to you, but it's basically a very simple classical algorithm to get your energy down further after you get the data from the QPU. Okay, after I've walked you through our pipeline, I want to show you some first hardware results, which are actually just fresh from the press. I think we just did them a couple of days ago. And for that, I want to show you data on the Sherrington-Kirkpatrick model. It's a very interesting model. It's coming from the area of spin classes. It's all-to-all connected. And you could also think about it as an optimization problem. And the coefficients, the couplings between the spins are actually drawn from a Gaussian around 0. And that makes it very interesting because now your system is very frustrated and the solution would be highly non-trivial. And what we are comparing in this plot is sort of the final energy we get after the QAOA versus the system size, different system sizes of the SK model instances, which we use for benchmarking. And here we are comparing random sampling. So you just randomly draw bit strings versus our optimization pipeline, which we call trying QAOA here, which is the red line, and the random sampling is the green line. On the very top, you see the average energy of the distribution you get from the quantum computer without post-processing. So this is raw data, and you can see here we have a slight advantage over random sampling. So random sampling is the 0 baseline, we have a slight advantage. And if we just look at the minimum energy we get from the quantum computer, things look a little bit better. So we can improve the energy with comparison over random sampling already in the raw data. And if we then add post-processing on top, we actually find the ground state for all system sizes. And this is true for random sampling and for the parity-twine optimization, which means either our post-processing was a little bit too smart or the problem sizes we've been looking at were not big enough. All right, so if you want to try that out yourself, feel free to use our new Qiskit function, which should be launched in a few weeks, which has sort of this whole pipeline integrated. Or if you're just interested in the compilation of the circuits, you could also use our ParityOS Twine compiler via our ParityOS web interface to get the circuits. To summarize, I showed you that with the parity twine compilation, you get the lowest gate count available in quantum optimization, and that we were already able to demonstrate that on large-scale quantum computers on hardware. So thanks to the team from Parity QC and also to our collaborators from IBM Quantum.
All right. Thank you. And we have still time for one question. Please. Okay.
Okay, very simple question. If I take, say, 60 qubits, right, the maximal number, I run this mean field AOA, which you mentioned. So for some given random configuration, I get a certain approximate optimal energy. And then I run your method. Do you see the improvement from quantum algorithm, or how they compare?
That's a very good question. So it depends a little bit on the instance, but in principle, we see an improvement over the mean field AOA run all the way to the end with using our quantum methods.
All right, let's thank the speaker, and we move to the last talk. All right, so the last speaker of this session is Alan Rosen from IBM Quantum, and he's talking about observable estimation in the absence of classical verification.
Perfect. Good morning. Yeah, so my name is Elon Rosen. I'm from IBM Quantum, IBM Research. And I want to talk about this paper that's linked here. This is one of a trio of papers that IBM put out about 4 weeks ago. And these papers are really trying to push the boundaries, push towards quantum advantage. Good. So first I want to thank our collaborators in this work. There's several institutions, particularly Algorithmic, who developed the circuits that I'll talk about today. Good. So this is a story about verification, about validation. So we want to use quantum computers for scientific computing, right? And if we're going to do that, we need people to trust the outcomes, right? If we tell a biologist or a material scientist some result, we have to trust that that result is right. Otherwise, we're just wasting time and money, right? The story I want to tell today, this is not a story today about quantum advantage, but I do want to say that these circuits are hard, classically. In particular, we have a family of circuits, and we can tune the classical hardness of those circuits. So we can go from classically easy regimes, where we do have a classical ground truth that we trust, and then we can push harder and harder circuits until we really don't have a reliable classical outcome. Now, does that mean there's classical intractability and possibility? I'm not going to litigate that question today. That's sort of the job of the quantum advantage tracker, right? This has to be a community-driven process where a lot of people can use their resources, use their techniques, and address these questions. As a community, we'll come to these decisions. What I can say is that these circuits have been on the tracker for several months now, and as far as I know, there hasn't been a credible classical result. Good. So we're talking about using quantum computers for scientific computing. In my opinion, there's sort of 3 pillars that we have to satisfy to make this really work. Okay, of course we need validation. We also need applicability. We need to do circuits that actually matter for real problems, real scientific problems, right? And then finally, we need classical difficulty, of course. I think everyone will agree here that there hasn't really been any demonstration of all 3 simultaneously. We're going to talk about validation today, but I do want to say that we're sort of trying to get very close to satisfying all these things in this work. So in particular, yeah, we talked about validation. We talked about classical difficulty. In some limits of the circuit I'll talk about today, we right now don't have a classical ground truth. Now, as far as applicability, these are contrived circuits. They're sort of designed for the purpose of the exercise I'll talk about today. But I do want to say that they are structurally very similar to real scientific questions. They're essentially Trotter evolution problems. So these are similar to problems that real scientists do care about. Good, so let me just briefly talk about the big structure of the circuit. So these circuits are perturbed mirror circuits, right? So if you're familiar with OTOX, these are a very similar idea. The idea of these circuits is that we'll have some sort of Trotter-like evolution step. Then we'll have sort of the inverse of that Trotter-like evolution. And then in the center, we have a perturbation. And the thing I want to point out is that we can tune the parameters. So in particular, we have L. That's essentially how many Trotter evolution steps we do per sort of quarter unitary block. Then we have delta, that's the strength of the perturbation. So importantly, if delta is 0, there's no perturbation, this is just a mirror circuit. And then finally, we have eta. And eta is what I'll call a scattering factor. It basically tells the circuit how fast it should scramble quantum information. So it also controls the difficulty of these circuits. Good, and then we're going to be running these circuits on IBM Boston, which is an R3 Heron generation processor using 56 qubits. And the error rates are, well, I'm impressed personally. The sort of composite error rate is about 0.15% per 2-qubit gate. Good. So we want to build trust through processes of error mitigation, let me start by talking about a heuristic approach, so a global rescaling-based approach. Good. So let's start by just going all the way. Let's go to very difficult circuits. So these are L=6 circuits. They have a very large perturbation. And let's look at classical results at different scrambling strengths. Okay. Now, if we go to very low scattering strengths, this is where tensor networks converge. And so we actually do have a ground truth in the extreme limit here. We trust this result up here. We know the tensor network has converged. Okay. And then let's look at another leading classical method, polypropagation. We don't really trust polypropagation in this low scattering strength limit. We think in the high scattering strength limit, it's probably close. We can't say for sure. We don't have error bars, okay? But we think, maybe this point is close to being right. Okay, but crucially, for neither classical technique, we don't have error bars. And so in the middle, at intermediate scattering strengths, I don't think anyone can look at this plot and say, I know the right outcome for this computation. And so let's bring in the quantum computer. So we're using global rescaling here. It's a very simple error mitigation technique. What we're going to do is go to the mirror point, delta equals 0, where we know the outcome should be 1. And we're going to just check how much of the signal we lose. And then we're going to go back to the finite delta and boost our signal back by that same amount. Okay? And now we have a quantum outcome. It agrees with the tensor network where we expect it to. Where we think the polypropagation method is close, well, we're pretty close to the polypropagation method. Okay, and in the middle we have something that looks like pretty sane behavior. Okay, but this isn't good enough. Can we trust these outcomes? So let's go through an exercise of trying to build that trust. So let's back off. Instead of having these L=6 circuits, let's back off to L=3, L=4. So now we actually have a classical ground truth. We can do tensor networks. We know those tensor networks converge. And let's compare those outcomes to the quantum outcomes. And indeed, they line up. Okay, great. That's not enough though. Let's go further. So this global rescaling method, this relies on the noise acting the same way as we change from the 0 perturbation limit to a finite perturbation limit, right? So let's check. Back where we have a classical ground truth, does this damping factor change between delta equals 0 and delta equals 0.3? And we can see here, it's very similar. Okay, but this still isn't enough. Let's try to go further. Let's go back to the hard limit, L=6. And let's just see, can we get consistent results? So I showed you before running this computation on IBM Boston. Let's try running it again on IBM Boston, but at a different gate time. So now the noise model of the system is different, and we get a consistent result. Once we go through the error mitigation process, of course. Okay, let's try running on a different device. Let's go to IBM Pittsburgh, consistent result. And we can even go further. We can synthetically apply noise to these devices and check, do we still get a consistent result? And the answer is pretty consistent. Okay, so this convinces me at least that of the considered methods, the quantum result is the most trustable. Okay, but this is a heuristic method. I can't draw error bars. I can't tell you for sure how close is this. So can we go further? Can we draw error bars on these computations? So that's where unbiased error mitigation comes in. So let me tell you about PEC in about 30 seconds. Okay, so the idea of PEC is very simple. We characterize the noise on the device. We quasi-probabilistically invert that noise. We run the circuit. We get an outcome. And crucially, rigorously, that outcome is unbiased, provided that our noise model is representative. Okay, so I'll be talking tomorrow a little bit more about PEC, a little bit more depth. But let me say, the thing I want you to take home today is that because this is mathematically rigorous, what PEC does is it converts the problem of validating the outcome, the quantum outcome, it converts that problem into the problem of validating the noise model itself. And if we can do that, then we know rigorously that we'll have the right outcome. Okay, so let's go through this process. I don't have time to go into full detail today, but let me say the noise model we use, it makes a set of assumptions about the device and about how we've learned about the device. And so what we do is we just go point by point and we test all of those assumptions. And that ranges from sort of simple small scale tests of is this condition noise well behaved, and it goes all the way to end-to-end tests. And we see consistent results across the board. And so we're ready now to move on to full PEC. And so now what we can do is we can pick a whole bunch of different observables. We can go through the PEC process, we can get results, and now crucially we have error bars. Now what we've done here is we've backed off again to slightly shorter depth circuits, L equals 2, L equals 4, where we have available classical ground truths. And so we can benchmark the PEC mitigated result against the classical ground truth. And in every case, we see that the PEC results are consistent within error bars. Okay. Now, what we ultimately want to do, of course, is to be able to do PEC in this classically intractable regime at large depth circuits. Now, right now, that's not something that we've accomplished. And the reason is just overhead. PEC comes with overhead. That overhead goes exponentially in the number of 2-qubit gates. And so it does become costly. But we have strategies to mitigate that. So in particular, PEC is only as good as the underlying hardware. What PEC does is it takes excellent hardware and makes it even better. And that's why I'm so excited about the future of our processors. So we'll be releasing a new family of Nighthawk processors imminently. And I'm very excited. These are very powerful devices. Secondly, we can work on PEC itself. So there are mathematical techniques to sort of accelerate the PEC process and allow us to quickly mitigate larger and larger observables. And then lastly, there are strategies that are sort of in between error mitigation and error correction, sort of hybrid strategies. So there's a recent paper, one of these three papers I mentioned earlier, talking about this kind of error detection scheme, and Joanna is going to be giving a workshop in just a few hours today about this result, how you can use Qiskit to run these kind of workflows. Great, so here's a link to our paper, Observable Estimation in the Absence of Classical Verification, and I think there's time for a question. Thank you very much for your time.
So one question before the coffee break. Ask quickly, so we will get quickly coffee. Anybody? Well.
Could you explain a little bit the model, what was unitary circuit is doing actually physically, and what was the scattering phase, how this unitary operator was constructed?
Yeah, that's a good question. So these circuits, let me go back. Yeah, so these circuits were constructed by algorithmics. So, I think ultimately I should refer you to their team to talk about the circuits. But I think the important part to say is that these are Trotter evolutions circuits. So we have these quarter layers U. And what you can see is that there's sort of on each side of the perturbation, the unitary is broken up into two approximately adjoint blocks. And at scattering factor 0, those blocks are actually equal. And so what that'll do is make an inner mirror of the circuit. And then by turning up that scattering factor, we're sort of taking that inner mirror away from itself. So the Trotter evolution scrambles quantum information faster and faster. And I think the important thing here is that the light cone of these circuits grows throughout this layout very, very quickly. That's, I think, the key factor.
All right. Let's thank the speaker. And then we come back 11:30 here for the next session. Thank you.
Okay, sorry.
I need to Bye bye. Thanks. Become an entertainer as well. Your own late night show. I got 10 minutes in my.
Hello, Henrik. Again. Yeah, good to see you.
So, yeah, one question.
Yep.
Yeah, it makes sense. Yeah, like one additional one would really help. I was already wondering we could have cabled up the session share also with this, but I think having just one.
Yeah, exactly. I want that's the one of the things I want. I want the session share to have this one, and then
one and bring him down to
yeah.
this table.
And another thing, I'll have this. Is mirroring what's going to be there. So that looks good. This looks
Perfect. I'll quickly use the restroom. But
yeah.
Okay.
This one.
Yeah,
for
I'll
this.
try to find Christian. Fabio and Anders.
Yep.
I'll try to find.
I'll just stay.
Yeah, okay, great. Okay, then I think we are ready to get started with the next session. So my name is Christian Andersen. I will be chairing this session on design and modeling, which is an exciting topic. We saw nice keynotes from Andreas and from Aziza, and they had beautiful chips. And from experience, you don't get beautiful chips like that unless you do some design and some modeling. So that's what we will do in this session. And the first speaker we will have today in this session is Mark Brias. Sorry, I butchered that, but yeah, take it away. And this will be a contributor talk. So all the talks here are 12 minutes, including questions.
Thank you. Yeah, is this on? Yeah, sorry, my name is a bit of a mouthful. So today, as Christian said, I'll be talking about like modeling loss in JTubers. So before we start, like just an introduction where I'm coming from. So I work at the Institute of Advanced Industrial Science and Technology in Japan, in the Kanto area. And it's in Tsukuba, which is, I'm not sure, well, we cannot say this, it's an hour and a half or so by train from Tokyo. And unfortunately, you cannot find Pokemons nowadays, but you can find very nice kind of like local food and our national lab and our brand new building in JQuat. So let's start with the talk. First, I'll give you a brief highlights of the theory that I'm using. Then, because we only have 10 minutes, I'll move quickly to some simulation and results and conclude with some remarks. So, it would be good if this, okay. So this is a kind of like a simplified JTuber. We have thousands of unit cells composed of like a Josephson junction and capacitances. So here the idea to include loss basically is to add dielectric loss as an imaginary component of the capacitance. Note that we could also add inductors, and then that with them they could also have certain kind of like loss. And once we solve the equations of motions, we have this kind of like metamaterial behavior. And we have then like an effective wave number that in this case would be complex because we're assuming these loss components. Yeah. So I'm not giving you the details how you obtain these equations, but basically Josephson traveling wave parametric amplifier like follows a traveling wave. Okay, so basically the wave evolves with the space, and then here I'm assuming the strong palm approximation, which basically means that other modes don't affect much the pump. In this case, not at all. So here what we have is like just the, let's see if, okay, maybe here's better. So because like now we have our wave number that is complex, then will appear this minus component, so it will be basically affecting like the loss. And then the solution will look something like this, where we have a certain kind of like loss decaying factor and a phase modulating term. Then, because like I want here to introduce some close expressions, I'm defining this effective pump amplitude, which is basically once I get the solution of my pump, I integrate over the whole device. And then for the signal, we have like this kind of simpler equations where we have the first term, the beta term, accounts for the wave mixing. And then the next term is the self-modulating. Similar, you can see that it looks very similar to the pump. So now it have a term that depends on the phase, and the red one is like the loss component. Then basically we express it in real valued functions. This is my chi's, and then change of variables, and you obtain this. You can see now that I rename kind of the loss component as gamma, and it's depending on like the pump strength, if you want, and this loss term, okay? And this is because usually this is how it appears in the quantum equations, if you want. So here, now we have like the full expression. So in order to be able to have a kind of quantum-like equation, we need like that the energy is conservated. So here basically the M is like the matrix that account for all the wave mixing and loss, and then the gamma here is like all this loss, it's feeding a thermal bath, a Markovian bath, okay? Then to solve this is like usual techniques. Basically, first we target the homogeneous equation, okay, like the term without the gamma and the b, and then we solve that equation and we obtain that the solution is a kind of a transfer matrix. And people who are familiarized with kind of amplifiers, they will notice that this term looks very similar to the gain profile. But in this case, we have this asymmetric gamma. So that's the difference of loss between the two modes. And then this extra total decaying term that just appears by solving the equations. Then to obtain the full solution, then we apply a green matrix or green function formalism. And then basically we obtain that the full solution is the homogeneous one plus a term that depends on the Markovian bath, which will basically be very important for the correlations. Okay, then this is an example of the signal mode, where now instead of matrix, I have the actual green functions here. And then the game, by solving this, will depend only on the first term. Now, just bear with me a little bit before we get to the simulations. So now we need to find the two moment correlations. So for each of the modes, we're gonna have the photon number, and the closed form will look like the ones on the top right. So basically we have like this dependence on the crossing terms plus like the path contributions, and the same with let's say like the correlations of the two modes, the mixing modes, which will look like the following. Once we have this, we can calculate many things, among them squeezing. So this would be the closed form of the squeezing, particularly when we evaluated the like the most efficient angle, if you want. This cosine term will become -1, and then we have kind of maybe a more usual expression with a -2, the anomalous term, and then the photon number terms. Okay, if you're not asleep yet, now we're gonna go to simulations for the last couple of minutes. So this is what it looks like for the gain. So here I'm putting a quite, I would say, unrealistic level of loss for our devices, but it's just to see the trend, okay? So I think that for most of our devices would be between the first two lines, the ideal case, which is all black, and then maybe second or third line. So you can see that for the gain, we have this usual tilting kind of like gain at high frequencies. And that's because that minus gamma I was talking about, that has certain asymmetry. And then we see that for this loss, gain gets maybe reduced of 50%, but the squeezing is much more reduced, okay? This basically emphasizes that how basically quantum effects are even much more sensitive to loss. Another way to visualize the squeezing as well is kind of Wigner-like functions, okay? So in our closed form, you can make use of certain kind of symmetries between the quadratures and simplifying the Wigner distributions as follows. And now we can see the quadratures between signal and idler at different frequencies. And as we have seen in many undergrad lessons, when you have more squeezing, you have these more ellipse-like shapes. I'm getting short of time, so I'll go a bit quick. You can then also calculate with all the correlations, the entanglement level. So at the end of the J-tuple, basically we have these two mode states. So the signal and idler have coupled, okay? And they can show entanglement. And then we can show this with logarithmic negativity. And here on the left-hand side, I'm showing how it evolves with the length of the device, and on the right-hand side, depending on like frequency. Similarly, we can study the purity of these two mode states, where one is basically we have a pure quantum state, that nothing is mixed in it. And then as soon as we have certain loss, what happens is that this noise is mixing with our two mode states, so they are not pure anymore. And I guess that the most interesting part is the left-hand side. You can see that as soon as we have a little bit of noise, this purity of the two mode states like really quickly decays, okay? So if you want to, I guess, study more of the quantum properties using this kind of device instead of the gain on the more classical terms, probably you want a short device that even the gain is small, like you can preserve more kind of this purity of those states. And I think that I'm about to to get out of time. So I'll just give you here the concluding remarks for the questions, and I'll thank you all for your attention.
Great. We have time for a few questions. We could also use a few volunteers to run with the microphones. So if you feel like a good runner, you can come. Otherwise, I will try to throw this around. Any questions for this talk?
Thank you for the nice talk. I was wondering, since you modeled the dielectric loss with this formalism, what else can you model? Let's say that, can you model the variation of the JJs and then get some closed form expression on the, let's say, fab spread and then mistargeting and whatnot?
Yeah.
To be able to understand the device a bit better. Thanks.
Yeah. That's a great question. I mean, like, I guess that the quick answer is like, yes, you can. The tricky answer would be like, I would have to think carefully. I don't think that you can find closed equations anymore. Okay, so unless you do unless your variation follows maybe kind of a Gaussian, something very nice that you can subtract. But let's say at the very beginning of the talk, like say, when you have these kind of equations in here without assuming even strong PAM approximations, then I can like just use full numerics, and then you'll have these massive like matrices of like wave mixing. And then from there, you would have to start analyzing like the covariance matrices of this kind of, let's say, you'll have maybe, take this with a grain of salt, but this kind of a transfer matrix. And then we'll have associated here certain kind of like correlation things. And then you'll get some numerics out of it. But the closed forms might be a bit tricky, I would say.
Okay, if there's a quick question, otherwise let's thank the speaker again. Skip it. And we can get ready for the next talk, if the speaker can come up. And we find the slides. So the next talk is by Harsh Arora, who will give a talk about light matter interaction in the dispersive circuit QED regime. And the slides are already there. Yes, perfect, great. So take it away.
Hello, everyone. Title of my talk is Light Matter Interaction in Dispersive Superconducting Circuit QED. Today I'm going to talk about a curiosity that I explored during the last 6 months of my PhD at the Indian Institute of Science, and I'll talk to you about where this curiosity got me, and I'll also talk about how this curiosity ended up with a sort of a different formalism for doing circuit QED. When you have dispersion, which we know is quite strongly present in most of our superconducting transmission lines and resonators. So just to give a bit of a context, let's start with this very simple lumped element model. It's quite ubiquitous. The way this works is that the transmon couples to a transmission line and it locally modifies the capacitance per unit length. And that leads to a charge-charge interaction where the charge on the local charge on the transmission line couples to the local charge on the transmon. Now, this transmission line with its these open boundary conditions implies that this supports an infinite set of harmonics that gives rise to like the usual cavity-like picture that we have. But a reasonable question to ask is, okay, yeah, you have like an infinite number of modes, but then how many modes actually participate in this interaction? Is there a cutoff? And if at all, do these superconducting properties of these transmission lines affect this interaction scale? Okay. So what do we know already? This is some of the work that Professor Hakan Turechi at Princeton did. But it's very important. It serves as a good playground to develop this theory from. So the way the coupling between the transmon and the nth harmonic scales as square root of the frequency of the harmonic times the mode amplitude at the position of the transmon. And it gives rise to this very peculiar looking structure where you sort of have a square root n growth initially, but then the square root n growth gives away and it gives rise to this 1 by root n power law. But look at the mode number. You really have to go to very high mode numbers to sort of have a small enough coupling. And the reason we see this power law decay is because at large frequencies, the transpon is essentially acting as a capacitive short to ground. And if you have to do a ballpark estimate for what this sort of a cutoff frequency should be, it's about 300 gigahertz, which is then above the superconducting gap of aluminum. So this raised a question in my mind, okay, we are dealing with frequencies which are above the superconducting gap, so maybe something has to change. Okay, let's explore this a little bit more. Now, one could say that, okay, look, Harsh, yeah, you have like strong couplings to high modes, but then detuning is gonna come in and save you. But then this is how the lamp shift versus mode number looks like. And we already see that we have strong contribution from modes which are significantly above the superconducting gap for both aluminum and niobium. So then this made me a little bit more curious. I was like, okay, this needs to we need to maybe reconsider the subgap theory to higher frequencies. Maybe you need to have an alternative formulation. But how do we do that? Okay. Well, in all of this, we are missing a very important clue. It's the fact that the mode that propagates is never transverse electromagnetic. It's quasi-TEM, simply because there's a difference in refractive index below and above. And because of this asymmetry, you get a tiny longitudinal component of the electrical field along the direction of propagation. Because of that tiny component, there's a component of the Poynting vector that's directed into the metal. Now, this implies that there is actually energy flowing into the substrate. Well, this is into the metal. We know this. And this energy is possibly dissipated within the London penetration depth scale. But how do we actually mathematically include this dispersion, the fact that the Cooper pairs are actually dispersing and possibly dissipating energy as well? Well, you just say that you replace your usual CPW impedance per unit length with this really simple cute formula. This is the usual magnetic contribution, but then you have a superconducting contribution which is weighted down by its surface participation ratio, which I think experimentalists will know quite well over here. And it's inversely proportional to the thickness of the film and the width. Okay, how do we build with this formalism now? You go to the frequency domain and you simply write down Kirchhoff laws, and you will realize that you end up with this dispersive wave equation where you have a frequency dependent refractive index, which depends on the surface impedance of the superconductor that you're working with. All of this is nice and fun as long as you're doing classical mechanics. But the moment you want to consider something quantum mechanical with this non-Hermitian wave equation, you're in a bit of a fix because, well, it's non-Hermitian, so you cannot straightforwardly quantize it. You typically have always been quantizing Hermitian wave equations. So now there's a problem, but the clue is well built in here as well. Above, let's say we talk about frequencies of the gap. We know there will be a resistive contribution. Since there is a loss, it's sort of tricky to describe it using a Hamiltonian formulation, but the clue is that you can always add loss by incorporating an environment. Okay, let's see how do we do that. Now I'm already jumping to a result in the work where we were able to actually recover the dispersive wave equation that I was showing you guys before using a Hamiltonian formulation. But the way it works is you have the usual circuit QED Hamiltonian where you have the charge and the node fluxes, but the charge is now coupled to a set of reservoirs, basically a collection of oscillators at all frequencies, but the coupling strength basically scales with the resistance per unit length that the superconductor provides. Okay, pretty interesting. But now here's the nice part. Since everything follows from a Hamiltonian, you can actually quantize this and you will actually recover the canonical commutation relations that you want, provided the surface impedance satisfies Cramer canonical relations, which is a fair enough ask. Okay. So just to give you a bit of a workflow of the way this formalism is working, we started with a wave equation that we thought we can't quantize, but look, we can. It actually follows from this Hamiltonian. And now what you have, the full Hamiltonian is simply the transpon and then the transmission line and the reservoir interaction and then the interaction between the transpon and the usual interaction between transmission line and the transpon. Okay, so the natural question is, okay, cool, what changes now? Okay, so the way it works is with this Hamiltonian below the gap, let's say we are talking at 0 temperature, below the superconducting gap, you recover a Hermitian wave equation for the node fluxes, which implies that below the gap, you recover your usual sum over eigenmodes picture. But above the superconducting gap, when you have losses and you are in a fix about how to write down the solutions, you recover a quantum Langevin type of equations where you have a non-Hermitian equation, but it's also driven. And it's exactly this inhomogeneous non-Hermitian behavior that saves you. This is very similar to quantum Langevin equations, where the equations of motions are actually damped, but there is a noise term which enables you to recover the canonical computational relations. But the clue here, the thing here is that it's deeper than that. It's deeper in the sense that I am not mapping the resistance, the loss rates to a jump operator. In this framework, we're actually non-perturbatively diagonalizing the interaction between the reservoir and the charge density. Interesting thing to think about here is that in presence of losses, since you actually modify your solution, one thing to think about is how would actually photons be propagating on a waveguide, because if you have a localized wave packet, it's actually spread in frequency, and that would imply that at some point the way you're describing your wave packet has to change because maybe some part of the frequency spectrum lives above the gap. Okay, what kind of results do we get? The first interesting result is, which sort of builds confidence in this theory, is that we tried and recovered the loss rates for the modes above the superconducting gap. Turns out it very neatly fits into a power law that is quite expected from Matthias-Bardeen conductivity. So, okay, that was quite reassuring. And these curves are basically placed on the basis of the center conductor widths. So the topmost curve is the center conductor with the thinnest center conductor. And as you increase your center conductor width, the loss rate also goes down, which is expected because the superconductor participates less and less in wave propagation. Pretty cool. Okay. So how do actually things change with regards to coupling versus mode number? Over here, you will see Gn versus N plotted below the superconducting gap for aluminum. The red one is for the thicker center-conductor and the blue ones are for the thinner center-conductor. Clearly, you see that the thinner center-conductor red shifts frequencies a bit more. All of these blues are before the reds, but it also reduces the coupling a little bit, and the effect is more pronounced near the gap. Okay, more confidence building in this work. Okay. Above the gap, what we recover are spectral densities because you have a continuum of modes. But the spectral densities for the two different center conductors look very different. When the superconductor is not participating as much, you recover very sharp-like features. But then if the superconductor is strongly damping the system, you sort of don't recover those sharp-like features and you recover a very continuous spectral density. So a question to ask would also be, how does this affect two-time correlation functions and whatnot? Okay. Now, well, again, about lamp shifts, we see an interesting 1/s scaling with the lamp shift where the thicker center conductor always sits below the center conductor, the thinner center conductors, and they are overall reduced with regards to the node dispersion case that we studied initially. Okay. Just some convergence plots, which is again suggesting that you have you sort of saturate to a lower value when you start including dispersion, and in turn considerably reducing the light matter interaction frequency. Just a bit of a summary, we sort of explored the curiosity I had. We ended up with a unitary quantum theory. It gives you no dispersion below, pure dispersion when there is no loss, and dispersion and dissipation when there is a lossy component. Some people that I want to thank, Professor David DiVincenzo, extremely instrumental in parts of this work. the team at Alice and Bob and my alma mater, Indian Institute of Science, and also Tata Institute of Fundamental Research, Mumbai. Thank you.
Great, thank you. If we can have the next speaker come up already, and then we thank Ash. We unfortunately don't have time for questions in this talk. So we move on in the program. The next speaker is Longxiang Wang, who will present his work on multi-photon processes for quantum control. Take it away.
Thank you, Christian. Thank you for a kind introduction. Today I'm gonna talk about the publication that got accepted this year about this series of multi-photon process for application in quantum. Go. And basically the idea behind this is really from the recent experimental work we did. I mean, also like a huge focus in our group was basically investigating these Fluxonium qubits, which is just a normal transform plus inductance formed by this Josephson junction array. Then a recent experiment showing that we can actually do this so-called sub-harmonic driving, where we basically put a low-pass filter to the flux line such that we can protect the qubit from decay, because you will not get this resonant transition. But in the meantime, you cannot resonantly drive it. So that's basically trigger this idea of the sub-harmonic driving, where we use this multi-photon process to really do the single qubit gate in general. But our experimental colleague do this experiment, especially for the spectroscopy, and found that actually the resonant drive frequency is not explicit at 1/3 of the qubit transition. And when doing this sweep in the amplitude and frequency, we actually saw that basically there's a difference between the numerical simulation and the experiment. And that's the reason why we need to develop this new framework to kind of explain the difference from the experiment. And the basic idea behind is really from this Flokai degenerate perturbation theory. And if you look into a very general periodic driven system, then it's always possible to do the Fourier transform to go this so-called Zambi representation. And the cause is that you go to some infinite dimensional space. And in general, here we implement this perturbation theory to identify the effective Hamiltonian of like the state we are interested in. And in fact, we can basically build up the description of the dynamics in this like reduced system, and by mapping this back, this inverse operator of the perturbation theory and also this MP mapping, we can really recover the time evolution in the real space. And we actually quickly test with, the most general case with this Rabi oscillations. And we have to identify this epsilon 1, which makes sure the degeneracy between the states that we are interested in. And in general, we just implement the framework we developed. And in general, it will give you this such a, messy term here to really tell you about what do your matrix element in the effective Hamiltonian look like. But in general, in the end, you get this 2x2 effective Hamiltonian, where in general, the resonant condition is really make sure by you enforce the diagonal term to be the same. And also the off-diagonal term will give you the typical Rabi rates in general. And we test this with the simple case where you only have a two-level system here. And if you go to really small driving limit, then you will see this envelope evolution, which gives you the population transfer from the ground state to the first exit state. But on top of that, there will be this strong fast oscillation, and this can be really seen if you go to this strong driving limit. And we test for different orders, and in general, when we go to really higher order, we can really recover these fast oscillations that in this basically this multi-photon process. And step from that, we actually go to the Fluxonium case and test basically by predicting the resonant frequency and Rabi rate from this effective Hamiltonian. Then afterwards, basically doing this map for different amplitudes, basically how good this theory can give you the best fidelities in the population transfer. But if you include this fast oscillation, it really predicts quite well with the optimal case, basically from the numerical simulation. And apart from that, we also do some pulse shaping here. And if you assume that you have some slow pulse, we can also omit the pulse shaping into this general framework and reach a better fidelity compared to the cosine pulse. And also I want to mention that we really tested in the experiment and really show a good agreement between the experiment and theory. And we basically, the case that we implement in our device is basically comparable to the resonant driving case, and we gain the protection of the T1 time of the qubit. And this framework can only work in the single qubit case, but also the two qubit case where you have this tunable coupler there, then you can drive the so-called I-swap gate, basically the swapping between two qubit sides with certain phase. And actually it shows like our framework can predict this resonant condition realize, basically Stark shift. And also we can really predict quite well about this leakage term in general. I mean, if you drive this coupler too strongly, then there will be some leakage from the qubit to the coupler side. And now to conclude this talk, I guess I've shown this general idea of the subatomic driving and also basically the perturbation theory that we built up to describe this dynamics. And actually the experiment shows that it overlaps with numerics. And we also tested in the two qubit case just with the numerical simulations. But I guess the next step would be try to do experimentally, try this experiment. And I guess that's all for my talk today, and I would like to thank to all the people from our group who contribute to this project, and I want to highlight one of our colleagues, who will give a talk about the fluxonium entanglement this afternoon, and I also want to advertise our poster where we also do a lot of works in optimizing of the transmol scaling chips. Yeah, thank you. Thanks you for the attention.
Great, thank you. We have a good time for questions. So raise your hands. We have a few runners now. So that's great.
Thank you.
Just speak. They will.
Thank you very much for this nice talk. Could you just kind of explain a little bit why this kind of like a Sambi or Sambe representation works that well? So compared to this effective Hamiltonian that you found?
Yeah, I think it's because when you do this perturbation theory, I mean, if you go to the effective Hamiltonian, your basis is just assume that you have a single component there. But essentially, this perturbation theory will map different bases into the single state, which will contain different frequency component. I mean, essentially, the integer multiplication of the drive frequency, such that you can recover these fast oscillations in general.
Okay, thank you very much.
Okay.
Great. We have a question here in front. Oh.
Miko was first.
Yeah, Miko was first.
Yeah, thanks for the nice talk. I just wondering about, as far as I understood, your theory is doesn't take the dissipation into account. But then in your plots, the simulation of your experimental results, I assume you did take somehow dissipation into account. Or were you coherence limited, or were you somehow limited by something else? That's question number one. And then the question number two, of course, is that how did you then take the dissipation into account? Because that's kind of interesting to me, yeah.
Yes, so I guess for the first one, I think it's coherence limit currently, because the numerics is basically the same, or basically even better than what we achieved in the experiment. And for the second one, I think it's a good question and it's hard to answer, because currently this Flockheim theory only works for the closed systems. And if we would like to go to some open systems, then in general, I mean, you can build up some Liouvillean, and you also use this Flockheim stuff to really predict things, but I guess the theory will be really, really complicated, I guess. Yeah.
Great. And last question to Mert.
Thank you so much for the nice talk. When you do the Schrieffer-Wolf perturbation theory, and especially in the strong drive limits, how the degree of perturbation that you can achieve, is it 2 or more, or are you limited by the degree of the perturbation, or the order of the perturbation? Sorry.
I think for the moment, like the highest order we can achieve is basically the 7th order. And if you basically go to even higher order, then just like the time of the computation that you need to take account into. And for the moment, we have achieved a really nice result in such a order. So I don't think it's basically limited by the order currently.
Can discuss that after
Okay,
the talk.
yeah.
Okay, thanks.
Can discuss later. Thanks.
Great. Let's thank the speaker again. And of course, spend all the time in the conference to discuss after the talks. That's also where we learn a lot. With that, let's welcome the next speaker, which is Alberto Del Angel Medina, who will talk about quantum electrodynamics with Josephson junctions. Oh, take it away. We should probably find your slides first, actually. They're there, okay.
Essentially just continue. Oh, they're
No.
backup slides.
Yes, so. They were almost there. Yes, good.
Okay, thank you very much for being here today. My name is Alberto. I'm a PhD student at Anton Fries Kockums Group here at Chalmers University. And today I will talk about the quantum electrodynamics that we have been developing for applications in superconducting circuits. So first, I just want to state the obvious, which is that superconducting circuits make up for excellent qubits for information processing applications, and that they are a consolidated platform for quantum optics. And the current state of the art revolves around minimizing the noise from the environment, maximizing the control that we have on our qubits, and also scaling them. And then at the core of it all is the theory of circuits, in which basically photons are described in terms of two scalar variables, that is the flux and the voltage. The fundamental block of matter is the Josephson junction, and electric and magnetic interactions with the two are given in terms of capacitors and inductors. So the way that we understand how the electromagnetic modes of certain environments like waveguides or cavities act on our qubits is basically through the ideas of black box quantization or the EPR approach, in which one basically gives numerical simulations from which one can actually obtain the equivalent circuit parameters that characterize the qubits, right? But as you can see, the underlying spatial profile of the electromagnetic modes plays a fundamental role. And there's a very nice, beautiful example from the Kirchmeier group from Innsbruck, where you basically have the transmon antennas exhibit collective behavior that is superradiant or subradiant depending on where you place them, but also regarding their relative orientations amongst one another. So let's just think of how things work in the other platforms. That is, when we're using qubits formed by atoms, ions, or quantum dots, the more natural description is the electromagnetic fields, where photons now are encoded in three-dimensional vector fields defined in space and time. Quantum matter is described through its charge and current densities, and the couplings are usually given in terms of the multiple moments of the latter. And the thing is that by accepting the vector nature of the photons, we're actually getting access to extra degrees of freedom that we can use to engineer more novel light-matter interactions or encode information into these ones. So for example, the simplest degree of freedom that I can think about of a field is its polarization, which can be either linear, circular, or elliptical in general. And then to give you an example, for example, if we have a quantum dot deposited in a photonic crystal cavity, it will emit either to the left or to the right, depending if I shine light into it that has circular polarization with left or right-handedness. And we can also, for example, think about, again, the collective long-distance dynamics of atoms that are coupled to optical nanofibers. And this is just an example of the nice things that you can do. So the question that I would like to address today is whether we can formulate a quantum field theory for superconducting circuits in which the Josephson junctions are explicitly coupled to the electromagnetic fields. And the answer is yes. And that on top of that, we can also discuss about the multiple moments of the Josephson junctions and some interesting physics that can come out of it. Okay, then just to give you a more concrete picture of what we have in mind, we imagine a point contact Josephson junction, which is composed of two superconductors that are sandwiching the oxide layer. This is not to scale. in which you have that there is a tunneling current density flowing due to the Josephson effect, and inside of which lives the superconducting phase difference, which is the degree of freedom of the junction. Outside, we have the electromagnetic fields that are generated by either the cavity or the waveguide, which is in itself characterized by its own dielectric function. Okay, so basically by employing path integral techniques and such, and choosing the appropriate gauge, we came up with a junction Hamiltonian that is composed of the standard kinetic and Josephson term potentials, right? Plus an electric interaction in which the charge imbalance operator couples explicitly to the electric field, and the magnetic term in which spatial gradients of the superconducting phase couple to the magnetic field. The degree of freedom of the junction in this representation is the gauge invariance phase difference. That is not only the bare phase difference, but it actually accounts for the vector potential, which is in turn canonically conjugate to the charge imbalance. And if we compute the Heisenberg equations from this Hamiltonian, we obtain the generalized Josephson relations, in which you see now that the phase evolves according to the electric field and not the voltage. And the evolution of the phase of the charge imbalance is not only given by the tunneling term, but also by the gradients of the underlying supercurrents that are nearby flowing the junction and the magnetic field. Good. So then what can we say about the junction now that we're talking about fields? Can we develop a new, a multiple moment that goes beyond the dipole one? And the answer is yes, through the action of a constant magnetic field. So to lay it out, you can consider the junction, and the idea is that you apply a magnetic field that is constant along a clever direction, in such a way that now the phase difference will develop a spatial gradient along the length that is perpendicular to the direction of the magnetic field. And this in turn translates into developing a non-trivial phase in the Josephson potential. If you solve the quadratic part of this Hamiltonian, you obtain normal modes, but you will see that now you have developed this, that they're explicitly varying in space. And if we go for the fundamental mode, you see that this has no variation at all, but then the first excited mode actually has a nice oscillation. Concerning the energies, the energy of the fundamental mode corresponds to actually the Josephson plasma frequency. And the energy of the first excited mode is proportional to that, but on top of that is proportional to a geometric factor relating the length of the junction and the Josephson penetration length. And then just to give you some numbers, for a 6 gigahertz plasma frequency, then the energy of the first excited mode would oscillate to more than 2/3 of aluminum's superconducting gap, which is prohibitively large. But the idea that I want to transmit you today is that at no point we are addressing the transmon with energy. We're building spatial correlations that we can develop the quadruple moment. And okay, let's just focus on the junction Hamiltonian within these two modes. And if we diagonalize it, then we obtain a set of dress modes, which are superpositions of the ground and the first excited state mode, And if we project these operators into the electric interaction Hamiltonian, we see that to first order, once we expand these Hamiltonians, we obtain the electric dipole interaction, in which the electric dipole moment of the junction couples explicitly to the intensity of the electric field. And the electric dipole moment of the junction is proportional to the thickness of the oxide layer. If then now you take it to the next level, we get the electric quadruple interaction, as I promised, in which now you see that the electric quadruple moment does not couple to the electric field in itself, but with gradients of the electric field. That is how the electric field changes. And you see that the quadruple moment is proportional to the area of the junction, and that you can picture it as just two dipoles that are pointing in opposite directions. Okay, so is there anything interesting that we can do? Well, the answer is yes. Think about a coplanar resonator. So according to the electric dipole interaction, again, the dipole couples to the field in itself. So if you wanted to trigger the junction by means of this mechanism, you would ideally like to put it in an antinode, which is where the electric field is the most intense, right? So that you maximize the coupling. But what about an electric quadrupole interaction? Again, I'm telling you, since this does not couple to the field in itself, but to gradients of the field. And it just so turns out that for a coplanar resonator, where the antinode is located, the gradient is 0, but precisely where the electric field vanishes, the gradient is the maximum. So you would ideally have to put it where you would expect the least to be excited. Okay, so we're reaching the end of the talk, and I will give you a brief outlook. So again, we developed this electromagnetic field theory for the Josephson junctions. We believe that these models can provide you more detailed accounts of dispersional losses, either due to the geometry of your qubits or the material responses of the electromagnetic environments. We think we can really incorporate the dielectric and the magnetic functions. We believe that this also allows us to think about more exotic light-matter interactions, where we can actually employ the strong coupling nature of qubits and mix it with the more interesting nanophotonic techniques developed in the other platforms. And we believe that since our theory is fully gauge invariant, that this may have broader implications in many body phase transitions, the renormalization of the energy levels of superconducting qubits, and of course, the ultra-strong coupling. This couldn't have been done with the help of my postdoc and supervisors, to whom I thank a lot. You can find the paper in the archive. It's currently being refereed. And if you would like to talk to me, here's my emails, so please give me a call. And that would be all. Thank you very much.
Great, and we have time for maybe a couple of questions. There's one already here.
Thank you for this nice talk. I'm an experimentalist at heart, so when I see your nice model, I'm immediately thinking, okay, can you also incorporate stuff like impurities in your junctions, which actually make your model less perfect in a way?
So the thing that we can do, again, is if you could provide the dielectric function, or we have means to theoretically compute the dielectric function incorporating that, yes. Like we can do Matisse-Verdin, stuff like that, if you need it. Yes.
Okay, great. Maybe one short question.
Hi, thanks for a good talk. How would you include, systematically include kinetic inductance and the coupling of flux noise directly into the system?
That's an excellent question. So when I showed you the bare multipolar Hamiltonian, the kinetic inductance is shied away because I replaced it by the Josephson penetration length, but we actually have it, and we computed it. And can you remind me of your other question? Sorry. That's a more different type of problem. But basically, this amounts to understanding how the gauge invariant phase difference couples to the external electromagnetic fields. Once you quantize them, that's the tricky part. But in principle, it can be addressed. Yes.
Great. Then let's thank Alberto again. And we are getting ready for Ibrahim Al-Youssef, who will give the next talk on Q-chip, I think is the name of the package that he will present. So take it away.
Thank you, everyone. I am Ibrahim, and today I will introduce you to Q-chip, a differentiable toolkit for modeling quantum devices. This talk is not as sophisticated as the talks we have seen today. It's about a new way of modeling quantum chips, software-wise. So in this talk, I will talk you through three main parts. First, I will explain what is Q-chip and its centerpiece, which is the chip, and finally end on some differentiability remarks. So what is QChip? QChip is a software, an open source Python toolkit that tries to answer the question, what are the main ingredients of quantum pulse level simulations that only the user can provide, and what can be abstracted away from the user? So the answer is the chip, the actual chip contains most of the physics. It contains the devices, it contains the drives, the couplings, it contains the classical control that couples to that chip, and the rest can be put in some engine or some software from which you can compute multiple stuff. You can ask about the statics of this chip, you can ask about some dynamics properties, you can transform this chip around, and you can flow some gradients through it. The thing that QChip is trying to do is how the field got from using these analog mixers and connecting these many lines to control a single qubit to now using this black box that you can use. You get a single line and you connect it and get everything. So what do we mean by devices, by couplings, etc.? Devices are basically what provide these local Hamiltonians, these elements like your transmons, your qubits, your resonators, etc. And couplings are how these pair interacts to each other. And drives correspond to the Hamiltonian term that couples your classical field to your device. And finally, the control equipment, which is the classical part of your signal, whatever delays between the lines, the crosstalk between the lines, etc. All of this get combined in this object called the chip, and it asks you what kind of approximation you want to apply, what kind of frame you want to simulate in, from which you can compute the rest of the physics. So let's talk about this chip. We'll talk about how you define it, what kind of study you can run through it. The way you define a chip in QChip is similar how you would describe it to a colleague. Here, for example, we have a 2-qubit chip with 3 resonators in the chip. Each qubit is coupled to a readout resonator capacitively, and the qubits are coupled through a bus resonator. And we have 2 control lines, charge drives, one for each qubit, and they have some classical crosstalk that we encode. All of this, I would like to simulate this in a rotating frame and apply the rotating wave approximation. Well, this is an interesting way of defining your chip, but sometimes you read some experimental paper and you see some drift frequencies and drift quantities. Or for example, when you do an experiment in the lab, you get the actual drift spectrum. You can say here, okay, given this drift spectrum, find me a chip that will mimic this spectrum. And also, if you are familiar with SC qubits, you can basically take your Hilbert space object and transform it into a QChip. Whatever the way you define the chip, it goes through an engine. This engine makes sure that your basis is compatible. It applies frame transformations to ensure you are in the frame you want. Sometimes you want to do it in the lab frame. Sometimes you want to do it in the rotating frame. It applies approximations that you choose. And finally, ensures your dissipations are consistent. At the end, you will get a resolved chip. This chip is ready for you to query. Now we will see what kind of queries you can ask. The first question you can ask, what are the chip statics? I want to ask, what are my drift frequencies? What are my conditional frequencies? What are my chi's, ZZs, etc.? You can also ask, if I sweep these bare parameters, what will happen to my drift spectrum? How would it change? Like some avoided crossing-like studies. You can also instructively see what happens to your Hamiltonian, how it goes through this rotating wave approximation, what terms that get dropped, and what is the unitary for your transformation that transform you between frames. You can also ask, what are the dynamics of the chip? And this is powered by 2 mature packages, which are QTIP and dynamics with a Q. You can input your expectation values and they will get transformed in the appropriate simulation frame and get back to you as you expect them. So for example, you will not see this fast oscillation that I got the first time I tried to do pulse simulations. Also, you can do a batch sweep, multi-D sweeps, and QChip will directly convert this to a form that dynamics or QTIP likes. not only you can study the statics and dynamics, you can say, I want to transform this chip. For example, you spend your time, you define your chip. You want to not change the topology, you want to change some numbers, some frequencies, some coupling. You want to add some noise, remove some noise. You can do that easily. Also, sometimes you want to reduce your chip. You built this big chip, but your study or your pulse level simulation doesn't care about all of the chip. So you say, I want to remove these resonators and remove this bus in between them, and you can do that adiabatically. So the effect of the resonator, some lamp shift, some T1s will get absorbed by the qubits, and some, if you have a bus between them, it will get removed and the direct edge will form. Sometimes you have this big chip that you created and you want to ask, well, I only drive one of them and I want to only care about the nearest neighbor, and it automatically will remove the farthest qubit and add new coupling lines if necessary. Finally, we can have some statement about differentiability. Q-chip is built to be differentiable end to end. So for example, you can have a loss that spans the statics, the dynamics, especially when using the dynamics backend. The guys have a differentiable solver, so you can run the gradient through that. You can also do multi-sequences and check the gradient for that as well. So for example, you can ask the question, I have some design spread of my variables and I want to see what happens to some measurable quantities. You can compute that gradient. You can also say, I have this pulse, this gate, and I want to see what is the gradient or the sensitivity of the fidelity. You can also have this multi-sequence calibration routine and compare the sensitivity of each one of them. So in conclusion, Q-chip combines all of your physics in the chip model. It is easy to build upon. You can use the built-in devices, and you can easily, in like one line, extend your new devices. The engine takes care of the bookkeeping, the frame transformation, the observable operations, and gradient can pass through the entire chip easily. It's open source on Python, and you can pip install it directly. You can here access this talk and some guides that get more details on what we showed here today. And thank you for your time.
Great, thank you for the talk. We have time for a couple of questions. I see in the middle.
Thank you very much for the nice talk. I'm wondering how many qubits can you have on the chip that you can simulate?
So this takes the standard scaling of the solvers like Q-tip or dynamics. I think, I don't have the number with me, but it's the standard. Q-chip doesn't add or reduce any cost from these solvers.
Good. I think there was one more. Same question. Great. Okay. Other questions? I had a question then. When you did this thing where you eliminated the some of the qubits, do you calculate then also effective couplings that come when you eliminate them, sort of an extra residual ZZ coupling that?
Yes, yes. You basically use Schreif-Wolf to find these couplings at effective G whenever you remove any direct.
I see. Great. Yes, makes sense. Good. Any final question? Yes, over there. Yeah, good. Tom.
Thank you for the talk. I wonder how can you treat noise spectral density?
Noise what?
Noise spectral density. Let's say that you have 1/f noise and one and white noise. How can you distinguish these two?
I'm not quite sure. The noise here comes through these Lombardian operators, so I'm not certain.
So let's say some of them could be correlated or non-Markovian, and these type of elements.
It depends how you model them. So what Q-chip is doing basically is taking the layer between you and the solvers. So however you would like to solve them in regular Q-tip or dynamics and how complex you want to write these collapse operators, here is no different. So I'm not sure.
Thank you.
Thank you.
Great. Then let's thank the speaker again.
Thank you.
Good. And we move on to the next talk, which is Oscar Watzfeld, who will talk about ZZ and ZZN couplings. So take it away, Oscar.
Yes, hello, my name is Oscar Watzfeld. I'm a PhD student here at Chalmers, and today I want to show you that modeling couplings on a large qubit chip is not as difficult as it may seem. So to achieve useful quantum computation, you need a large chip with many qubits. As you scale up a qubit chip, however, you face a challenge. You are adding more and more ways for qubits to couple to each other. These couplings may be always active and thus may constantly degrade the performance of your chip. One such coupling is the ZZ coupling between two qubits. And more generally, you can have a Z to the N coupling between N qubits. Unless these are controlled, they may induce phase errors in your computation. But if they are controlled, they can be used to implement 2-qubit gates and multi-qubit gates. The work of modeling such couplings can be difficult, however, since it involves many qubits and many excitations. Luckily, though, we have found that this modeling is less challenging than it may seem. So here's a quick review of ZZ couplings. In this system right here, we have capacitive couplings between qubit-qubit and qubit coupler. When we diagonalize this system with respect to the couplings, we find the rest energies of this system. These energies can be expressed using the Pauli-Z operator in the computational subspace, that is. And in general, you will have a term proportional to Pauli-Z on both the qubits. This term makes the frequency of one qubit depend on the state of the other. Similarly, if you diagonalize a larger system, you will find not only ZZ couplings, but ZZZ couplings and any Z to the N. Later, we will compute these couplings. And for that, we should define what a small ZZ coupling is. So by demanding that the error from ZZ should be smaller than the error from decoherence, one can estimate that the ZZ coupling should be somewhere below 100 kilohertz. So let's say that a small ZZ coupling is one that's far below 100 kilohertz. Let's now take a system with any number of qubits. Here is a Hamiltonian, which describes the rest energies in the system. The first terms gives us the frequencies. The second terms are the ZZ couplings. But what are these ZZ couplings and higher? It's a bit hard to see their effect, so I want to rewrite this Hamiltonian in a way which I think makes that easier. We can rewrite it using the number operator defined on the second line. In this form, the first term gives us again the frequencies. The second term will add an energy shift if both qubits I and j are excited. So the effect is that the frequency of one qubit will be shifted when the other one is excited. Oddly enough, the coefficient in front here is often also called ZZ coupling. You can easily translate between this and the previous Hamiltonian, but from now on I will call this right here ZZ coupling. So beyond these we have 3-qubit couplings, 4-qubit couplings, and so on. Those are more complicated than the previous ones, but do we really need to consider them? I will use delta En to describe the energy shift from the 3-qubit couplings up to the n-qubit couplings. For example, let's imagine we have 4 qubits, and we look at the energy of the 1-1-1-1 state. Since all the qubits are excited, we will have all the frequencies, all the ZZ couplings, and then we will have 3-qubit terms and 1 4-qubit term. Delta E4 in this example is the sum of the 3 and the 4-qubit contributions. And the subscripts here are simply the qubit labels. We studied the approximation that all of these couplings between 3 or more qubits can be neglected. Equivalently said, these energy shifts, delta E, is negligible for all n greater than or equal to 3. And what we find is that this is a valid approximation for typical transmon grids. More specifically, by typical transmon grid, I mean this system here. We have qubits and tunable couplers. Both are modeled as transmons. The black lines are capacitive couplings, and the layout is this square connectivity. As a restriction, we look at the dispersive regime, where capacitive couplings are weaker than the tunings. And for these kind of grids, we have both numeric and analytical evidence for this approximation. So let's start with the numeric evidence. Here we take 6 qubits, 7 couplers, a total of 13 transmons. We compute all these energy shifts, delta E3 up to the delta E6. And we do it in a parameter regime, which is summarized here. We consider the qubit detunings to be both smaller and larger than unharmonicities. We use the couplers to minimize the Z between nearest neighbors. And the capacitive couplings take on these values here. So far, we've sampled 300 systems in this regime, and the rotating wave approximation has been used. But in the future, we will sample more systems, and we will not use RWA. So what did we find? Well, as a result of tuning the couplers, all the Z between nearest neighbors were smaller than 20 kilohertz. All the Z couplings between more distant qubits were sub-kilohertz. And these energy shifts, delta E, they were all smaller than 3 kilohertz. So 3 kilohertz is small compared to this 100 kilohertz I mentioned earlier. But let's look at the histogram of delta E below. We see that, in fact, it's typically far smaller than 3 kilohertz. So according to this data, in this system, the approximation is valid, is accurate up to around 3 kilohertz. Moving on to the analytical evidence. Using perturbation theory, we can treat a grid of any size. So we can consider delta En for any n greater than or equal to 3. We take any such energy shift computed to the 4th order in the capacitive couplings, and we show that the lowest order contribution is at 4th order. So to 2nd order, to 3rd order, delta E is 0. But at 4th order, we can say that the contributions have this form. GQQ represents capacitive qubit-qubit couplings. Delta QQ represents energy differences over these couplings. Notice here that the couplings between qubit and coupler, GQC, delta QC, do not contribute. This ratio, GQQ over delta QQ, is typically small. Let's plug in some realistic values to get a rough estimate. 5 megahertz for the qubit-qubit coupling, 100 for the delta QQ. That makes half a kilohertz. So perturbation theory would agree. Delta E should be small. Now that we have seen the evidence for this approximation, what can it be used for? We can use it to simplify the work of modeling qubit chips, and it can help teach us something about how to design them. So here I'm giving you one example of how to use it. We ask, how do the energy shifts from multi-qubit couplings affect 1-qubit gates? For simplicity, I take this system here with 1 driven qubit surrounded by its nearest neighbors. Using the approximation, I can write down this Hamiltonian where the 3 or more qubit couplings are discarded. And in this example, we take the fidelity of an X gate in the case of equal ZZ couplings. Assuming that the ZZs are significantly weaker than the drive amplitude omega, we can expand the fidelity to lowest order according to this. We see here that the variable is the ratio of ZZ over the drive amplitude. Here I'm plotting the infidelity as a function of ZZ. We have 3 different drive amplitudes, and you see their corresponding gate times in the legend. The relationship is clear. As you increase ZZ, the infidelity goes up. If we want a fidelity of 99.99%, then we look to the red line. It tells us, for instance, that if we have a 25 nanosecond gate, so the blue line, then we should make the Z-Z coupling smaller than 40 kilohertz. The point here is that an analysis like this is easier to make when we can neglect the couplings between 3 or more qubits. So to summarize, for large transmon grids, there are many couplings that one could worry about. Beyond the familiar Z-Z couplings, there are more complicated multi-qubit couplings. Luckily though, these are typically small in a dispersive regime, and we can use this to simplify models, which then makes it easier to analyze, for example, fidelities related to Z-Z couplings. This is a work in progress, so if you're interested, stay tuned for the preprint.
Great. We have time for questions. There's a quick one from Andreas.
Did you consider how you could mitigate these effects using dynamical decoupling?
No, I have not considered this.
Good. There was also a question here. Yeah.
Thank you, Oscar, for this nice talk. I may have missed it, but when you were like mentioning that the phase shifts, like the energy shift of like higher kind of like more and more qubits, like they are small for an arbitrary n. Like usually when you have this kind of like, let's say a large sum, a sum of like small terms doesn't mean that is a small number. So yeah, I guess if you can comment if you have checked how this series converges or anything like this.
So you're saying that, for example, a 3-qubit coupling could be small, but you could have many of them.
Yeah.
Yeah. Yeah, it's true. Here I'm not going into. I'm kind of, as you can see, I'm taking the cumulative contribution of all the 3 or higher. So one could go deeper and look at the individual K-body term, for instance. And then you could perhaps see, hopefully, an exponential decay of these. And then you could say something about, relate that to the combinatorics and say something about how the total might add up. Like the issue here would be the 1, 1, 1 on every qubit state, for instance. That would have all the 3 body, yeah.
Okay, great. And final question all the way in the back.
Yeah, so thank you. Very good talk. So did I understand correctly that before doing the perturbation theory, when you had the lumped element circuit, there was no capacitance between non-nearest neighbor transmons? And if I understood that right, why is that so?
Yeah, I guess I approximated them away. No long distance capacitive couplings. Those would change like the theory. I'm not sure if the assumptions of the proof are still fulfilled, but that would be interesting to look at, yes.
Thank you.
Great, then let's thank the speaker again. Good, and our final speaker of this session is Alessandro Rinieri, who will talk about 3D superconducting parametric coupler. Take it away.
Thank you. So today I'm going to be talking about a 3D superconducting parametric coupler based on the link for a configurable Bain splitter and squeezing interactions. So this is quite a mouthful, but it all boils down to a recipe on how to design a parametric coupler that doesn't interfere at all when in idle and gives you the cleanest interactions when driven. And let me start with something obvious. So far, we have established that superconducting QPUs are very good. They can do very fast local gates. However, in order to deliver a utility scale and fault-tolerant quantum computer, it's becoming more and more evident that we need some sort of coupling between these QPUs, and this coupling must be shaped in such a way that it doesn't interfere with the actual computation when idle, and it basically delivers the wanted cleanest possible interactions between QPU and QPU when driven. So how do we connect these superconducting QPUs without inheriting nonlinearities from one to the other? And we do that by choosing the appropriate parametric coupler. Introducing the LINC, the linear inducting coupler, which has been first developed by Matey and Ali at the Yale group, and I strongly encourage you to give a look at this kind of paper. This LINC is basically a squid threaded by a linear inductor in the middle, and when driven, it gives you the linear inductor basically is masked by the outer junctions, and when undriven, it becomes completely linear at its biasing point of phi dc equal pi over 2. And what is most interesting with this parametric coupler is that the drive frequency selects the process, not the hardware geometry. So depending on how you drive the coupler, you can have beam splitter or two-mode squeezing interaction. And I want to stress the fact that this linear inductive coupler is very linear and state independent when performing beam splitter interactions. So if you compare the LINC with the well-known superconducting linear asymmetric inducting element, or snail in brief, you can see that the monochromaticity of the LINC, apart from when you drive it at the resonant frequency of the LINC itself, is much better than the snail. And also the snail doesn't have, the LINC doesn't have this state by state G-beam splitter dispersion, whereas the snail does. And so how do we engineer a LINC effectively to connect two QPUs? And at this stage, I want to stress that the QPUs, we are completely agnostic with respect to their architecture. They can be transmon-based or they can be bosonic-based QPUs. So we want to have a stack that is tripartite. It has a beam splitter band at the lowest frequency, a two-mode squeezing band at the highest frequencies, and in the middle, a Purcell isolated environment in which your QPU modes and LINC modes live. And we engineered that in this kind of four-step loop. We choose the three circuit parameters that identify the LINC itself: the Josephson junction energy of the outer junctions, the capacitive energy of the whole circuit, and the inductive energy of the center inductor. Then we map the geometry to the mode participation performing eigenmode HFSS or your software or of eligibility simulations, and then we validate the behavior of omega with respect to the flux and the static anharmonicity with respect to the flux by artificially changing the value of the outer junction linear inductance. And finally, but not the least, we do a package iteration where we engineer the flux delivery line. And to make things more clear and put them in a better context, let me provide you with this scenario, a LINC for connecting two bosonic 3D QPUs. These QPUs have been developed by a colleague of mine at Superconducting Quantum Materials and Systems Centers that have been proven to go up to the 20th Fock level of encoding in a linear resonator enabled by parametric pump with an ancilla qubit. Why this architecture? Well, these two bosonic modes are very high coherence and putting a link between them can have the two be entangled or swap information on demand. And although that's the final goal, the easiest middle step to assess and to evaluate and refine the link behavior is to engineer a test bed that it's easier to and cheaper to fabricate, that can be made out of completely aluminum, and shows a coax drive pin and bonding wires to this CPW launch pad, which then is going to basically start the whole flux delivery line. And these two dual stub elliptic cavity that basically are placeholder for those very high coherent bosonic QPUs that I showed you before, and are coupled to the link by these cavity coupling irises. And the link itself, the on-chip part of this package, you can see features a full flux delivery line made up of a balloon that changes the circuit from a CPW to a CPS configuration, a stepped impedance stop bell filter, which provides the Purcell isolation of the two QPUs plus the link frequencies, and the link proper with the flux, with the coupling tree here and the flux delivery loop here, coupled to a transmon to assess and evaluate the DC bias coupling by using a 3-tone spectroscopy, 1 tone to the link, the second tone to the transmon, and the third tone to the readout resonator. So to basically walk through the 4 points that I highlighted before, we first do eigenmode simulation versus the linear inductances of the outer junctions, and then we fit them to the frequency and anharmonicity models that are provided in Matey's paper that I cited before. And we see that there is a very good agreement with respect to theory, and we can extract the effective EC, EL, and EJ coming from the distributed environment in which the link is immersed. And then we evaluate the beam splitter and two-mode squeezing couplings by performing the same energy participation simulations. And we find that it depends strongly on the iris area, because it depends on the static G3 with mixing coupling that is given by capacitive means typically. And we also look at the Purcell isolation, how well we engineer the filter stack that comes before the flux delivery line in order not to have the quantum processing unit leak through the line through which the link is biased. And finally, the hardest part is that we need to effectively assess the flux drive of this link, because so far we have looked only at eigenmode simulation. So in this full driven model treatment of the flux delivery engineering, we find that there is a design pressure point. So the link operates in this very nice linear when idle and non-linear when AC driven, only if it is differentially driven. And the differentiality or differentialness is provided by this RC over D ratio that needs to be minimum. So it means that the two currents that are circulating in the outer junctions are equal and opposite. And we see that if we inject a pure differential drive, apart from a neighborhood in which the link frequency is excited, the phase drops and the currents and the phase drops on the outer junctions are indeed equal and opposite. But when we look at the full line, we see that this is not quite the case. And the reason why I have very 1 minute. Okay, so let me go very quick through this. The reason why this happens is because the flux line has got mode itself. So it has some common modes that are excited and that couple with the link non-negligibly. In particular, there are very nasty low frequency modes that are have very low quality factor and couple strongly to the link, and which you can see here drive the currents on the same direction. We would like them to be flipped and going in a circle and not have any current in the middle inductor. And how do we mitigate this? How do we prevent this from happening? Well, we have to engineer another kind of filter to put beforehand in order to trap this kind of modes before they reach the link proper. And with the help of one of my fellow students, Pietro Faraggiana from Pisa, I was able to find this kind of interdigited filter that is a common mode reflection-based filter that traps inside itself common mode and prevents them from propagating through these differential lines. And we have realized this kind of filter on a sapphire substrate, and we are in the process of integrating it into our Purcell isolation stack, and to see if this is an effective way to trap these common mode, spurious common mode excitations before they come to the link. So just to conclude and to summarize everything, the main result is that this link testbed now has a closed loop between circuit theory, 3D electromagnetic extraction, and package level flux delivery and engineer. And what is next is that we need to integrate this common mode filter into this flux delivery line to suppress this kind of parasitic common mode excitation, and then to fabricate this design.
Great. We can have one quick question. If not, I think people are excited for the lunch. So then Stefan has a few practical works before lunch. So,
Exactly. Just some practicalities, essentially. So the next session in here will be at 4. Before that, we have lunch now for 1 hour until 2. Then we have workshops, poster session, and coffee break. And then we'll continue. For the poster session, if you have a poster for Wednesday, please go downstairs now, place it somewhere on one of the available stands. There is a poster award for Wednesday, for Thursday, and an audience award. For this, there is a jury going around checking your poster. For the audience award, you can ask people to heart your poster in the app, and there will be some prizes given out on Friday. For the workshops, we have the 4 workshops today. There is the Q-Blocks workshop in Scania at 2. That's out here to the right-hand side. Then at close to 3 to 55, Zurich Instruments in that room, Cruise upstairs, and IBM's workshop is downstairs in Palmstead near the entry. We will keep that slide open, so just in case you forgot, you can check in here and see. We'll also have people with signs guiding you to the workshop, so you'll find it. If you register for it, or if you're on the waiting list, both cases, you can come to the workshop and go there, and we will kindly ask you to please go there, because otherwise you're blocking people's space. With that being said, let's grab lunch. Thanks for joining in here.
I think we should slowly start now the next session, although I think there is still plenty of people outside and I hope they will join us soon, because it's a pleasure for me to announce now our next exciting talk after actually also the very exciting poster session, which I was very pleased to see that there's so many posters in the packed session. But now looking forward to now in total 8 talks about high fidelity control and readout. And we start off with Pascale Scalino, and who will tell us about fast hardware efficient superconducting qubit measurements with non-perturbative cross-care coupling.
Junction
Pascale,
readout. So yeah.
Junction readout in short. Stage
Yes.
is yours, please.
Thanks a lot. Thanks for the kind introduction. And let me also join the other speaker to thank the organizer for this really great opportunity. So today I would like to tell you something more about what we call now junction readout, which is a proposal from the group of Alexander Blay of about 2 years ago. And I would like to start with already the slide, otherwise maybe it will be too long at the end. I will not have time to thank all the people involved in this work. And of course, Alex Ottman from Alexander, they did all the theory proposal and help us to finalize the experiment. And also Peter from Riken and my group in EPFL, they did the experiment. So junction readout is a proposal in the context of transmon qubit readout. As we know, there have been a lot of progress in the last year concerning readout, but there are still quite a lot of limitation, because despite all of this progress, it's not so common to have high fidelity and fast, and also from the perspective of technology, how involved it is still, would be nice to try to understand how to push it forward. The problem that we try to solve mainly is that the same interaction that nowadays we are using to engineer cross-care, the dispersive interaction, is a transverse-like interaction, and this gives us some drawback that the community know quite a lot. Just to name a few: parcel decay. And the qubit, the Dresser qubit, still has a kind of a resonator component that scale as G over the tuning, and this is what gives us the parcel decay. We also have what is called a critical photon number concerning the dispersive interaction, but it's not the end of the story, because actually, as we have seen in the recent year, if you try to drive your resonator stronger and stronger, you may activate those multi-photon resonance that brings you very fast out of the computational space, and so promoting those multi-photon transition. And so this limits quite a lot the power that you can have in your readout resonator, and this brings also parametric amplifier and so on. Of course, the community is trying to circumvent this problem, and there has been proposal how to try to implement a kind of alternative readout to try to solve some of those aspects. And here I cite just those two. There are many other. One of the most promising is what is called the large detuning readout. And here the idea is to really detune your qubit and your resonator quite a lot, and this will dramatically reduce the onset of mist. Another possibility is to engineer the interaction. And here the idea is to, instead of making use of just transverse interaction, to try to engineer a nonlinear cross-care already in the beginning, which is not going to be perturbative. And this is actually what we are trying to do here with the junction readout. So let's start easy. So this is a standard transverse coupling between the transmon qubit and the resonator, which we can write down simply like a kind of coupling strength, J, due to the capacitive interaction, and then the charge operator on the transmon and the qubit. What we will want to start to look at is a system like this, at least as a building block. So there is a transmon qubit, a resonator, and now they are connected by an extra Josephson junction. And the interaction term in the Hamiltonian now is intrinsically nonlinear. It's the cosinus of the phase operator difference, okay? So we want to see what happens when we start to work with this, and at the end we will combine the two. So let's start to work with our junction. This is the total Hamiltonian of our system. Here we have just expanded the cosinus nonlinear term of the interaction before. And so if you expand it using trigonometric relation, you get a cos-cos term and a sine-sine term, both of them appearing here with the minus sign. And of course, if you now start to understand a bit more in detail what each one of those terms is going to bring into your readout toolbox, this cos-cos term you can expand. And at the end of the story, if you consider just the transform two-level system, you can rewrite this introduction as a cross-care interaction between the resonator and your transmon. And this is actually the term that we want to use to implement quantum demolition readout. But now this interaction strength is not coming perturbatively from transverse interaction and dispersive limit, is intrinsically built starting from a nonlinear coupling. So it can be also quite high, as we're going to see soon. On the other side, we have this sinus-sinus term. And if you look at it more carefully, it's going to give you such a term, which is pretty similar in terms of structure to what you get if you consider a capacitive interaction. A capacitive interaction is going to give you some J charge. This is some EJC from the junction phase operator. And if you replace, of course, this low amplitude mode operator there, you see that in terms of those operators, you get this structure here. And I'm preserving here the complete expression, but in the beginning we will work just on the co-rotating frame. In the beginning we will neglect the counter-rotating term, which at the end of the story we are going to play a very important role in our coupling scheme. Okay, so let's now try to couple both together, and here is where the capacitance start to play again an important role, because now from this sinus term, we know that we are going to get, as we have seen in the previous slide, this term. From the capacitive side, we get a very similar term. And both of them, they are of the kind of transverse interaction. But the very important point here is that they come in this global Hamiltonian with different sign. And so now the idea will be, let's try to find a configuration where we can try to balance those two terms, to try to cancel completely this transverse part of the your interaction Hamiltonian. And what you are left, if you are able to do so, is this cos-cos term, which is going to give you this not perturbative cross-care interaction. So why this is important? Because in this mist process, of course, there are different processes that play an important role. But if you try to actively find a configuration that cancel this transverse part of your Hamiltonian, what you're doing, you are completely, at least, eliminating the possibility of such a transition. Doesn't mean that you eliminate completely the mist process, but at least you push far apart the critical photon number, which represented the onset of the mist. So this plot is coming from this very nice work from Alexander Belay group. In this plot, what they try to do is to calculate what is the critical photon number in the sense of the mist, so the onset of the mist process, by comparing dispersive readout and junction readout, both of them kept with a pretty similar cross-care interaction. Of course, as you see in this axis, they are changing the frequency. This means that for the dispersive interaction, they have to also renormalize, change also the coupling strength in order between the resonator and the qubit in order to keep this cross-care 9 MHz. This is not the case of the type of nonlinear interaction that I just showed you, which does not depend at all by the detuning, so can stay big. And so what they see, the conclusion that you can get from this plot is that the critical photon number that you get for the junction readout is systematically higher respect to what you get with the dispersive interaction at the same cross-care coupling. So intrinsically, it seems that this junction readout is more robust against mist. And of course, the other prediction that they made in this work is that now, if you really try to find the configuration that completely cancel this exchange term in your Hamiltonian, this sinus-sinus charge, now you can also build in situ a parcel protected system, because that is what, I mean, is part of this amplitude. So if you cancel this term, your system for the specific balanced condition is going to be protected against parcel decay. So this is the device that we implemented in order to try to study this system. This is the first generation device, but designed and implemented by Guillaume, my PhD student. So if you look from without zooming in, so just from this picture, it looks like a standard device. So, you know, there is your lambda over 4 resonator, there is a capacitive coupling with your qubit. Of course, the difference is that now, if you zoom in here in this region, you see that there is not just your standard squid that you're going to use to tune the frequency of your transmon, but there is another junction there, shunting galvanically your redout resonator with the body of the transmon. So this is really the only difference respect to a standard device. So this is what we call the coupling junction, is what is going to give you this term in the Hamiltonian. This squid there is there in order to be able to tune the frequency, and especially what are the 0 point fluctuation of the phase of the transmon that will allow us to test this Hamiltonian and not just to realize a single instance. So now we have a tuning knob in order to change the frequency and change the impedance, effective impedance of our transmon, in order to try to understand if the prediction and the behavior predicted by this Hamiltonian is according to what has been predicted. But of course, as soon as you look at these devices, if you are familiar, there are some serious issues that we will try to solve in the future, and I hope that will arrive at the end of my presentation with at least the new generation of device that at least solve this problem. Let me mention this problem is that if you look carefully, because this is a lambda over 4 resonator, there are 3 loops in this device. 2 are gigantic loops, are indicated one with red and one with blue color. And then there is the small loop from the squid. So of course, this is not what you want to have in the future to create a scalable system that you can use seriously for quantum computing. But the fact that those loops are so different still allow us to implement a systematic study effectively tuning just the squid. Because actually, in terms of current, the periodicity that you have for the big loops are of the order of tens of microampere. Instead, the periodicity that you have for the small loop are of the order of milliampere, so you can really separate very well them. So we will keep an inter-edge flux quantum in the big loop and just effectively tune the squid. So for our preliminary investigation is more than enough. So the first kind of study that we implemented was, of course, tracking the qubit frequency as a function of this flux, tracking the anharmonicity of the transmon, and also extracting what is the cross-care shift coming from this junction readout. And of course, there are already, okay, before pointing out the non-trivial part concerning this cross-care shift, let me also mention that the line that you see on top are global fit, from which we extract all the parameters of our global Hamiltonian. So, you know, just to give you an impression, this junction for the junction readout, it has a energy of the order of 4 gigahertz, the capacitive part instead of the order of 80 megahertz. The impedance, the effective impedance of the mode of the resonator that we're using, which is going to play also an important role, is roughly 70 ohm. So the non-trivial part, if you are more familiar with standard transversal interaction, is that now by tuning the frequency, for example, of the qubit around half flux quantum, so pushing the qubit farther away respect to the resonator, which is around 70.5 gigahertz here, we have actually that our cross-care shift is increasing, non-decreasing. So this is really the fingerprint, the signature that we are not dealing with standard transverse interaction anymore. Why it is increasing the cross-care shift in this case is because you know, is given by this very simple expression. By changing the flux in our transmon, we are changing effectively what are the magnitude of the 0-point fluctuation of the phase. So this is our effective tuning knob in the system. So let's try to make sense of this chi shift. So now we have fitted all the parameters of our Hamiltonian, so we can try to plot the different contribution in our interaction Hamiltonian. So those are the data that I showed you in the previous slide with the same fit on top. And now in purple and in orange, you see the contribution coming from this non-perturbative cross-care and this transverse coupling. So as you can see here, so the data are following quite close the shape of the purple line coming from the cross-care, but of course there is a gap here, and this gap is due to the fact that actually, despite we are close to the balance point that should cancel completely this, we are canceling, as we have defined, this transverse coupling, but looking specifically at the co-rotating part. What we were neglecting till now was the counter-rotative term. And actually, what one can see is that, of course, the purple one is the shape of the cross-care that you expected, just renormalized by the impedance, as we pointed out before, of the transmon. But the orange one, if you don't neglect anymore the counter-rotative term, this is the global expression. And now we are close to the balance point. So what we are imposing by tuning our parameter is that this term is going to be 0, but this is still left there. And usually for standard circuit QD transversal interaction, we apply quite often the rotative wave approximation. So this counter-rotative term that we also call two-mode squeezing term usually is neglected because at the denominator you have the sum of the two frequencies. But despite that, here we see that actually close to the matching to the balance point is going to be the dominant part that you cannot neglect. So this specific shape of your residual transversal coupling is coming from your two-mode squeezing. So given that we have all the parameters, we can ask, okay, by tuning our external flux bias, can we meet at all our balance point? And this is what we try to answer with this plot. So here we are just calculating this matrix element as a function of the flux applied to the transmon, and when this goes dramatically to 0, are the point where you expect to see the balance. So that you are canceling effectively the co-rotating term in your transversal Hamiltonian. But at this point, where you want to operate your system, you still are left with the counter-rotating term that are determining, they're an important part of your chi-shift as a function of the frequency of the qubit, and still you're left with the positive part, so which is this very big cross-care interaction. So the question that we ask after this is, of course, if we try to sit at this balance point, the prediction that has been made for the first work are satisfied, namely, are we part-cell protected, and what is the missed resilience at those balance points? And so what we try to measure is the T1, so the relaxation time, and we measure it by trying to excite the transmon through our flux line, to our feed line. And so by doing those measurements, you can extract what is this induced part-cell decay. And the first thing that you notice is that actually at the balance point, you don't have at all the maximum of T1 that you were expecting. This is what at least we were expecting. So by canceling the transversal interaction at the balance point, we were expecting to have maximum of T1 around this point. And why it is not so is because, again, of this two-mode squeezing term that we were neglecting in the beginning. So around the balance point, you cancel this one, but you're still left with this. And of course, this is non-zero and create U parcel decay there. But if you deviate a bit by this, if you deviate by this balance point, both of those terms, they have a non-zero numerator. And now, of course, you can have a condition when this global amplitude is going to be 0. And this happens exactly at the frequency where the qubit will have, of course, at this flux. Okay? So those two-mode squeezing terms that we were neglecting in the beginning are very important. Of course, now you can also have a very easy interpretation of those frequencies of the qubit looking simply at the coupling scheme, which is nothing else than a parallel between a junction and a capacitor. So building an intrinsic notch filter, and when the qubit frequency is hitting this frequency, you have parcel protection. So we have pretzel protection, but not where we were expecting to have, and we understand now why. What about the missed protection? And so, of course, the group of Alexander Blay ran this simulation to try to understand what is the critical photon number. And around the balance point, we are quite safe, around 60 photon critical photon number. But the specific configuration that we have realized present to nearby this balance point to missed line, some transition that actually reducing the critical photon number right around this balance point. Instead, at the point where we get maximum protection for parcel, we get also something around 60 photon. So we decide to sit at this point. Around this point where we are parcel protected, those are the parameters of the system. Of course, it's not a fantastic qubit, this first generation is around 27 microsecond, T1. And the other important, very peculiar feature, and this I think I need to close soon, is that now, due to the junction coupling, our readout inherit a very big nonlinearity. How big? Or the order, for the specific value of the junction coupling, of the order of 1 megahertz. So we decide to try to explore this feature in order to implement bifurcation readout of our qubit. And so now you have a nonlinear resonator. If you as a function of the frequency, as a function of the power, this goes toward bifurcation. And so, but now the bifurcation region is different according if the qubit is in a ground state or in the excited state. So if you sit down, if you park your readout frequency in between those two, now, in case the qubit is going to be in the ground state, you stay in this lower branch, having a few photons in your resonator. If the qubit instead is in the excited state, you're going to have around 20 photons in your resonator. So this is the idea of this bifurcation readout. And those are the performance of the first experiment that we implemented in this specific configuration. I don't go in detail for time reason, but please ask me later if you are interested. Long story short, for this specific balance point, T1 parcel protected point that we were operating, we are able to get something like 99.4% assignment fidelity in 86-second integration time. The empty time for the resonator is around 120 nanoseconds for the specific kappa that this resonator has. If I have just 1 minute, no? What are we doing after? Solving the loop problem. How do we solve the loop problem? This is also in the proposal of Alexander Blay, the first paper. Instead of having 2 different sets of junctions, you just have a single junction that is going to give you both, it's going to play both of the role. It's going to give you enough nonlinearity for your transmon, but also it's going to be the junction coupling. And in this way, you solve actually the loop problem. Those are pretty recent data. Of course, you don't find any number for the fidelity. So we have implemented this new generation of device, and the work are in progress to try to characterize this. I finish with the outlook, and thank you for your attention.
So thanks, Pasquale, for the very clear talk, which doesn't leave open so many questions.
Super. Yes.
So I guess there is time for one short question, I'd say. Please, you first.
So in this junction readout, you should have a common mode because of this connection between 2 nodes. How do you simulate that common mode?
So you missed? No, okay. So in this specific way to build the junction readout, which consists in using a shunted to ground transmon and a lambda over 4, there is not a common mode. So there is not a low frequency mode that is going to mess up stuff. If you use a lambda over 2, or you use a floating transmon, in that case you are in trouble.
Yeah, I'm talking about floating transmon.
No,
but
in our case it's different. So we really, actually the first generation was in this way, it was not usable at all. So we moved to to this novel device design, so yes.
Thanks.
Yeah.
Sorry, we don't have time for more questions, but Pasquale is certainly around.
Yeah.
And so let's thank Pasquale again for the very clear talk. And then we move on to our next talk in this session, which is definitely a shorter talk. So it's about stressed state relaxation in coupled qubits as a source of 2-qubit gate errors. And I would welcome now Ruxia Wang on the stage. And once we are ready with the slides. Nope. Yes, so now we can start. So Ruxia Wang from Beijing Academy of Quantum Information Science, please, stage is yours. You have 12 minutes or 10 minutes if you want to have questions, please.
Good afternoon. My name is Ruixia Wang from Beijing Academy of Quantum Information Sciences. Today, I would like to talk about the dressed state relaxation in coupled qubits as a source of 2-qubit gate errors. So here is a short version of our story. When the 2-qubit interact with the coupling strength G, the ordinary dephasing noise at the frequency of 2G will open a new dissipation channel. So we usually do not budget this channel. So in a dressed system, we have to consider several dissipation channels, such as T1 for the noise frequency, for the noise at the frequency of omega plus or minus G, the T5 for the noise at a very low frequency, and T1G for the noise at the frequency of 2G. So the S2G is important in this talk. So here are several 2-qubit gates we use every day: the CZ gate, the CR gate, and the Ashen gate. The details are different, but they share a common moment. When the 2 qubits brought into a strong interaction, when we operate the 2 qubits, the 2 qubits with 2 qubits gate, the 2 qubit will be brought into a strong interaction, and at that time, a new error channel will be turned on. So our question is not which gate is the best, but it is when the interaction is on, which noise frequencies actually hurt the gate. So let's first see the gate error model. The transversal noise can cause the energy relaxation and dissipation, and the longitudinal noise can cause the dephasing. And besides the dissipation, there are also some coherent errors, such as leakage error, crosstalk error, and so on. But for real device, there is always some extra noise at specific frequencies. So in this talk, we will discuss about such kind of the frequency selective error channels. The realistic spectrum looks like this. So at the low frequency, we have the 1/F flux or charge noise. So at the high frequency, we have the quantum noise and thermal noise. So in between, from several megahertz to several tens of megahertz, we sometimes find some noise from the electronic devices, the TLS or spurious modes. And this band is easy to ignore because it is far from the qubit frequency. It does not look like a T1 problem. And it is not quasi-static. So it also does not look like a T5 problem. But for real device, there will always be some noise at these frequencies. And a coupler-mediated 2-qubit gate sometimes have the coupling strength G around 10 megahertz. So the dressed splitting 2G is just sits in this window. So before we go to the 2-qubit gate. Let's first recap the driven single qubit. So without a drive pulse, the Z noise only defaces. But when we apply a resonant drive along x-axis with the Rabi frequency omega, the quantization axis in the rotating frame will become the x, and the rest states is plus and minus x, and the same Z noise becomes transversal to this axis. So when the noise has a frequency at when the noise spectrum has a weight at the frequency omega, it will induce the transitions between minus x and plus x. So this rate is gamma omega. So this is why the spin locking is a noise spectrometer, because when we tune omega, we can read S omega. So the question is there an analogy of the T1 row problem, of the T1 row process in a 2-qubit system without a drive? So the answer is yes. When we apply the FSIM gate, we park the 2-qubit on resonance and turn on the exchange. So in the single excitation manifold, the computational states 0, 1 and 1, 0 will hybridize into two dressed states, tilde 1 and tilde 0, with splitting 2G. The fluctuations between the qubit-to-qubit detuning is longitudinal in the lab frame, but it is transverse to the new axis. So if there is a noise at the frequency of 2G, it will induce the transitions between tilde 1 and tilde 0. This is the dressed state relaxation, the T1G process. So this figure shows the shape of our engineered flux noise, and the Bloch-Redfield theory gives the definition of gamma G. In the classical limit, so we can model gamma G as equal up and down bit flips. So in this work, the authors have given us the results of the relationship between the gate error and the white Markov noise. So as an extension, when there is a noise at 2G, we give the gate error, we give the relationship between the gamma G and the gate error. So epsilon is a Pauli error, and this error depends on three things. So the first is the noise at 2G, the second is the gate time tau, and the last one is the coupling strength G. So next, let's see the experimental results. So our device is two transmons with a frequency tunable coupler. We injected the noise on 1 qubit, and the Gaussian white noise is bandpass filtered, and it is only on between 5 to 20 megahertz. And then gated, so it is only injected when the interaction is on. So we measure these two rates with the same noise. On the left, it is a single qubit spin locking circuit. It gives the gamma G. And this is a 2-qubit swap exchange. It gives, the left one gives gamma omega, and the right one gives gamma G. The shaded band is the noise, is the engineered noise, and the squares is R gamma omega, and the dots are gamma G. So these two rates have the similar behavior in and out of the noise band. And we fix the frequency at 15 megahertz, and here the gamma omega and the gamma G grew linearly with the noise power, and these two slopes are almost the same. So we want to know how this gamma G shows up in the 2-qubit gate. So we measure the 2-qubit gate error with the XEB circuit. So the noise is only on during the 2-qubit gate and not during the single qubit gate. So on the left, we sweep the gate time tau, and the dots are Pauli errors, and the solid lines are the theoretical predictions. And on the right, we sweep the noise power, and the gate error still grew linearly with the noise strength. And it matches the same formula. So now both the gate time tau and the noise power G behave as we expected. So next, let's see the coupling strength G. So when the 2G in the passband, the XB error tracks the rate predicted from gamma omega. So when we push the 2G to 30 megahertz, so the noise-induced gate error vanishes. And at the low frequency side, so we see the gate error does not drop as we expected. That is because the finite length pulse can still sample the nearby passband noise. So the practical message is simple. If there is a structural noise like this, we can tune the coupling strength to move the dressed splitting out of the noise window to protect the gate fidelity. So this is the summary. We give the quantitative gate error induced by the gamma G, and it is universal across various physical systems. I would like to acknowledge Professor Fei Yan. He proposed the idea and supervised the whole process. And Dr. Jia Yuding helped me set up the experiment. And Dr. Chen Lu Wang and Professor Haifeng Yu provided the chip. I also would like to thank the SQC lab at BKS for making this work possible. That's all. Thank you.
So thanks for the very interesting talk about the noise performance of coupled qubits. Is there a short question? Otherwise, we are running out of time again. I don't see any, so let's thank Ms. Wang again. And with that, we are coming to our next talk, which will be given, just a moment, by Yuan Gao, who is already on the stage, and it will be about ultra-fast single qubit gates through multi-photon transition removal. The slides already up, so please, you have 12 minutes in total, 10 minutes plus 2 minutes question would be the ideal case. So thanks, please, stage is yours.
Okay, hello everyone. My name is Yuan from Research Center Jülich in Germany. And today I'm going to talk something about some ultra-fast single qubit gates. So we know in the superconducting platform, one of the advantages is the qubit gates is fast, and we can run some deeper circuits. And we always want to improve the gate speed because that mitigates some decoherence error. However, when you're trying to use really fast gates, we see that the leakage error become large and large. Luckily, we have the drag technique, which we can reduce the components in the unwanted transition and got some leakage reduced. However, we still see that even with the drag technique, when we reduce the gate time, the leakage is still coming up really fast. We are able to reduce a little bit, but it doesn't work for arbitrary short pulse. So that's bring interesting questions. In this strong driving regime, when the qubit gate is really short and the driving strength is really high, where does this leakage come from? Because we apparently already reduced the most important transition from 1 to 2 transition, and the drags start to filling. And why is that? And how we can solve it? So our work actually answered those questions and found out a good results. We achieve around 6.8 nanoseconds single qubit gates, both pi and pi half. And we benchmark them and got about above 99.98% single qubit gate fidelity. And we keep the leakage below 2 × 10⁻⁵ for a really long domain. I'm gonna give a pretty intuitive explanation why this pulses work. We also have a theoretical work that explain in detail how this pulse shape is derived. So if we look at normal driving Hamiltonian, we will see there's normally 2 parts. One is the qubit energy, qubit Hamiltonian itself. Another part is driving Hamiltonian. And if we expand them, we'll see that the leading term is actually 1 to 2 transition, and that's solved by the drag. And if we we're trying to understand why the drag works, we'll see that it's actually acting on the spectrum that dominates the transition, the omega r, and we add notches in the frequency domain around the delta, which is the 1 to 2 transition frequency. However, if we do in the Schiffer-Wills transition, we try to diagonalize the Hamiltonian, we'll see there's even more leading terms that coming up immediately. That's basically the multi-photon transition from 0 to 2 and 1 to 3. And those are dominant by 2-photon transition and doesn't appear in the omega spectrum, but omega square. That is different than other previous work. They always focus on an omega spectrum and try to do some frequency domain optimization. So if we mimic the same correction or same drag technique, we can also do this recursive drag. We can apply the notches in the omega square spectrum to remove those remove those 2-photon transitions. So if we combine the multi-photon drag and the single photon drag together, you got your new pulse that is insensitive to most of the transition in the 3 leading terms and reduce the leakage in the really fast single qubit gates. So to characterize that, we first need to measure the leakage. However, normally the normal method is to use leakage randomized benchmarking. That suffers from incoherence accumulation because you need a large number of Clifford gates. That's not a single qubit gates because 1 Clifford normally corresponds to more than around 2 single qubit gates. So you need a really large number of single qubit gates to accumulate a small number of leakage. It's really inefficient. So we also introduce a new way to measure those leakage coherently. So as you can see from the Sheffer pattern on the left, this method actually coherent accumulate those leakage into different states, and you are able to extract the leakage error accurately, even below 10⁻⁶. So you can see the comparison between the leakage randomized benchmarking and the amplified leakage error. They show the same trend. They gave the same result, and it's even more accurate because it's less sensitive to the thermal noise. So if we compare them, we can see that within 300 gates, we are able to accumulate the leakage around 50%, but for leakage randomized benchmarking with more than 700 Clifford gates, you can only accumulate about 1%. So with the method developed, we can calibrate the gates. We have those effective calibration routine, and we can also scan the gate length and compare with the numerical simulation. We will see that we have an excellent agreement of the pulse parameter with the numerical simulation, and compared to drag, we achieve at least 2 orders of magnitude in the leakage reduction. So here we show the randomized benchmarking results from both normal RB, leakage RB, and also purity RB. And we can analyze the error budget. We will see that this pulse-shaped arc works for both pi and pi half gates. We are achieve above 99.98% in really low, really fast single qubit gates for both pi and pi half, and maintain the leakage at really low level due to thermal excitation. And with this result, we can safely answer those questions I bring in the beginning, that what is happening in the strongly driven regime, that is not a single photon transition that people work on in the omega spectrum, but rather multi-photon transition that you need to work on the omega square, and later maybe even omega cube. So with this is the summary, and I would also want to thank my group in PGI 13, and also our collaborator in PGI 8 from the Research Center Jülich. Thank you.
So thanks a lot for the talk about how to remove leakage errors by proper pulse shaping. Please, the stage is open for discussions and questions. I see one, Chris.
Hi, thank you for the nice talk. When you're getting down to such short pulses, how much is the sampling rate of your electronics playing into the fidelity that you get?
Currently, we're using Zulich instruments, and the sampling rate is 2 gigasample per second. I think they also can do some upsampling later. So.
Is there any further question? Here is one. Here is 2 actually.
What would be the effect of the rotating wave approximation? You're getting close to the.
Sorry,
limit.
could you say it again?
Because what would be the effect of the rotating wave approximation, kind of being at the limit or coming closer?
I think in our theory paper, it's also discussed whether this is breaking the rotating wave approximation. I think we are still in the safe limit. And I think later we can see from the simulation. If you are kind of breaking rotating wave approximation, the higher rotation, higher oscillation term will drop in, and you will see that the population will start to oscillating in some frequency, which you can't see from the simulation as well. So this simulation is done by the charge basis transmon simulation, and without rotating wave approximation.
Mm-hmm. So maybe quick, Saya, you had one? Yeah. Okay. Otherwise, let's thank speaker again for the very nice talk. And let's move on to the next speaker, which is Stefano Poletto on unlocking a fast adiabatic CZ gate and exact residual CC cancellation between fixed frequency transmons using a floating tunable coupler. Long title, but I guess it will be a clear story. You'll soon see it. Please, Stefano, stage is yours.
Thanks, Stefano, for the introduction. And a special thanks to the committee who organized this great conference. It gave me the opportunity to be here with you, share, I have to say, for the first time, this kind of results that we got recently. It's about Let's see, yeah. It's about a fast 24 nanoseconds adiabatic CZ gate who allowed us to achieve a fidelity above 99.9%. So I have only 10 minutes, so I go straight to the point of what is the talk. If you have more information, there is the link there or our paper. My talk is divided essentially in 3 parts. I want to give you an overview of what is the trade-off we started with. Right? So we go to our system. And finally, I give you an explanation how we tune up the gate and what are the experimental results we got up there. So the problem we start with, or the opportunity we had in front of us, is that usually on 2 qubits connected by tunable coupler, we have 3 main important parameters we try to achieve. And the optimization of these parameters lives in different subspaces. So one is the z equals 0 condition. That is usually found when the cubic qubit, the unit is larger than harmonicity of the qubit. So we have what we call the straddling regime. The second condition is a fast gate, so fast dynamic phase accumulation happens when the cubic qubit unit is larger than harmonicity. So already here you see the tension between 2 things, right? We have to choose if we want to be good, right, gates, fast gate, or if we want to have a good isolation and idling. And the third condition is usually to have a adiabatic gate, we need a good energy profile, and these lie on usually complex layout. All the figures here I take it from a nice paper of Feiyan, where he explains very in detail what it is. This work, he wants to close the gap. It's not implementing every single independently, but having one device that can achieve all 3 at the same time. Our system is a floating tunable coupler in a symmetric configuration. Floating tunable coupler you see in the yellow line, it has 2 pads where each pad is connected to 1 transmon qubit independently. And the energy profile and the 2 excitation manifold is the big image I put there. So here I use the labeling cubic, comma, tunable coupler. So the red line is a adiabatic line for the 1-1 state. And then we have the 2 excitation 1 qubits, that is the blue line and the green line. So the x-axis is the tunable coupler. We are using a fixed frequency qubit and moving only the tunable coupler. The vertical line on the left is where the idling is z equals 0 condition. In this specific configuration, the symmetric configuration of the tunable coupler, the g equals 0 condition is below the qubit frequency. So it's different from the ground that we're used to have above qubit frequency. But what you notice in this energy distribution is mainly that the 1-1 transition, the red line, right, sits on top of everything else. And there are not anti-crossing. When we move the tunable coupler close to the qubit, there are no anti-crossing. It's very smooth. And the phase or the dynamic phase accumulation, that is the difference between the red line and the reference line, the sum of the 1, 0 and 0, 1. So it's the gray area color there where the arrow is. It keeps going. So there is not a limit at some point it's stabilized. So it's a kind of unbounded phase. And the fact that we have fixed frequency qubit, we can reduce the noise that comes from that specific flux loop. So that is the system, and this is the experimental validation that we have large phase accumulation and idling z equals 0. The top plot on the left is a spectroscopic measurement of the 2 qubits, the orange and the blue line, and the green is the tunable coupler. The bottom plot is the measured dynamical phase accumulation, and the gray solid line is a joint fit of the 2. So what we notice is, first of all, that the dynamical phase accumulation goes to 60 megahertz here, and it's limited only by the fact that the tunable coupler, its maximum frequency is close to the blue to the qubits. But we have devices where we measure up more than 100 megahertz dynamical phase accumulation. And the zoom in the ZZ, it's near the 0, and you see that he's crossing the 0. So we have these 2. We have a fast gate, we have the battery trajectory, and we have ZZ equals 0 at idling at the same time. So when we talk about adiabaticity, it comes to our mind, right? So what is adiabaticity? And we are used to say it's move slow, right? You have to move slow your Hamiltonian. So how slow it is, there is an equation there that defines what is adiabaticity, but we like to introduce this d factor or adiabatic factor, that it's essentially how fast the Hamiltonian is changing versus the parameters. In this case, we have only the tunable coupler frequency. So it's the ratio between the one divided by the energy gap. So the D factor is essentially a metric that quantifies the non-adiabaticity of a transition. So we have a target state, for example, the 1,1, and we see how much is that D factor compared to all the other states. Larger is this D factor, more non-adiabatic is the transition. So it means we can leave something behind when we do the evolution. The plot on the left, on the top, is an hybridization plot. It's the state 1,1. So on the vertical line, the gray, right, close to 2.6 gigahertz, where it's idling, and you see that the red line, so the 1,1, is completely pure state. When we move the tunable coupler closer to the qubit, all the other states has to be hybridized. So the new adiabatic 1,1 is not anymore an 1,1 in the state we're using, it's the adiabatic 1,1, where it starts to be hybridized with the others. And the plot on the bottom is the adiabatic factor for the 1,1 state, plotted versus all the other two excitation states. So here I'm using exactly the same colors of the two, so you can see. The highest D factor is the blue that correspond, if you see, at the energy state, the 2, 0 of the qubit. While the second and the third highest D factor is the green and the olive colors that correspond exactly to the 2, 0 and the 0, 1, 1. So there is even the tunable coupler involved. And what I want to highlight is that hybridization itself, it's not enough to explain non-adiabaticity, because those two lines, the second, the third, the green and the olive, has roughly the same D factor, but if you look at hybridization, it's completely different. The green is almost 0, while the olive is pretty large, it's around 0.3. And this is because the energy gap we are looking at, it's the important thing as well. So the adiabatic factor is something more than just a mathematical, right, theoretical numbers we put there, but it's something that can really predict what actually leaks. And leaks, for me, it's larger than the leakage we are used to. It's even leaving something behind. This adiabatic evolution is moving too fast, we leave something behind. So we are using here leakage amplification measurement. We take it from this nice paper down on the left, the reference from IQM, that it allows us, right, by repeating the pulses, the flux pulse, and here we are using 20 nanosecond pulse. By repeating the pulse with some delay that is variable, we can identify where the system leaks and how much it leaks. So the plot at the center, where it's experimental, right, he highlights the 3 most largest leakage. What I really like at this kind of measurement, the leakage amplification measurement, is more than only identify the leakage, it tells us what is the frequency it's leaking. There is 1 over that time, essentially. So the 3 main leakage here is the 0.2, the 2.0, and the 0.1 with the tunable coupler. If you look at the adiabatic factor, are exactly the 3 largest adiabatic factor, exactly in the same order. So this factor is definitely more than a mathematical thing. It's something that tell us, right, what to expect. So we can design our devices even based on the D factor, and we see which one of the Hamiltonian is the best for a kind of adiabatic evolution. So now that you know the system, and I claim I have fast gate, has a nice evolution of the adiabatic trajectory, right? Everything looks nice. So we start looking at a simple pulse. We use this Fourier pulse. It's inspired by the work of Martinez and Geller, right? What is used the Flavian paper, but it's a sum of cosine terms. Here we're using only 2 terms. So we have a A1, A2 factor to adjust to optimize the gate. E1 is fixed, there is just normalization, so we are changing for each duration of the pulse, and we go from 90 nanoseconds down to 30 nanoseconds. By each duration of the pulse, we change the parameter A2, and we look which one has the highest fidelity. So the plot, the main plot color in red, he has the RB, and interleaved RB, that is the solid red, for this gate versus the duration of the pulse. So what I want to show here, highlight, is essentially that even with a pulse that is straightforward, just the sum of 2 cosines, and the only parameter we optimize is an amplitude, right? Already with this pulse, we have an adiabatic gate that it goes down to 32 nanoseconds, and it has a fidelity between 99.5 and 99.8 in the whole band up there. So if we want to go faster, you see that around 32 nanoseconds, the fidelity goes up because it's all a leakage. And at the point, we have to do something else. We introduce the adiabatically shaped path, the AWP. Again, this is taken from a paper of Ian. It's very nice work up there. The idea is you take the path you want to implement. For us, it's a simple cosine. Take the derivative and divide by that derivative by the de facto. So essentially, it tells us where the de facto is largest, where there is the highest probability of leaking of the system, just go slower. When it's not, just go faster. So we have this de facto that we calculate by design and by measurement, and we divide by the other one. So what we got here are all the black points. As before, we have RB, interleaved RB. The solid is the interleaved RB. What I want to highlight is for any duration of the AWP perform better than the Fourier path. And this allows even to go faster because where the Fourier path breaks down because you have leakage, the AWP still keep working. I'm going to highlight here that we have a gate as fast as 22 nanoseconds. I want to highlight this is an adiabatic gate at 22 nanoseconds. And we are putting just 2 nanoseconds on padding, no more than that one. What you notice on the leakage, the measurement down, is a comparison with this leakage amplification measurement, or what the two errors are. So the 24 nanosecond parser, when it's implemented with the Fourier, the red side, and with the AWP, the black side. You see the difference in the leakage up there. So the final slide essentially is how we tune up the high fidelity gate. Essentially now that we have 24 nanoseconds, we go through the same procedure it was before, that tune up. The first 3 points is exactly the standard procedure I explained before to tune up the gate. But now we do an optimization over the 6 parameters that define the path. So it's this de factor, then it's the conversion from frequency to flux. Finally, we do brute force scan, and we got this 99.92% of fidelity of 24 nanoseconds adiabatic gate. We repeated this over 8.4 hours, and the system is quite stable. So this is on the paper on the Superman if you want to know, but it's just a comparison between the symmetric layout and the asymmetric layout of the floating tunable coupler. It just rotate a little bit. In the asymmetric layout, the G equals 0 condition now it's above the qubit frequency. It's what we're used to think when we have grounded tunable coupler. So the gate is implemented by moving toward the qubit. And you see the main difference is the red line, that is the 1-1. In the symmetric layout, it's very smooth, it's above energy. There is no anti-crossing. While in the asymmetric layout, there are anti-crossings, and the ZZ, the dynamic phase accumulation, is way more limited and bounded. And this is in the adiabatic factor. The y-axis is exactly the same scale, so you can compare the one versus the other. So with this, I just conclude my talk. If you wanted to know more, there is the paper down archive, that is the link, and if there is time for questions, I'm here, or you can send me an email or chat with me later. Thank you.
Thanks. So thanks, Stefano, for the very nice talk on how to get fast and high fidelity gates. Unfortunately, there is no time for a question, but Stefano is around for the rest of the conference, I guess. And so we move on. And thanks, Stefano, again. And move on to our next speaker, who is Alpo Vellima. Sorry for the mispronunciation, most likely, who will tell us about mitigating couple leakage and flux-tunable superconducting qubit architectures. Please, stage is yours.
Thank you. Hello all. I'm Alpo from IQM, and I'll talk here about coupler leakage mitigation, and I can already perhaps thank my co-authors here. Starting with our architecture, it has demonstrated high fidelities in our recent publication. More about that, please attend Antti's talk later here in SQA. We have almost the same architecture in use, except we use coupler readout and drive lines to more precisely study this topic. And instead of a large QPU, we focus on a single 2-qubit pair and extend the findings to large systems. So what I will show in this talk is that the impact of residual coupler population for NISQ applications, QEC, and error budgeting. Briefly about our implementation for CZ, we use flux pulses, qubit flux pulses align 1, 1, and 0, 2 states, while the coupler flux pulse initiates the ZZ interaction. And these are the tuning knobs in frequency landscape, so the coupler is pulsed from below the qubits. And as a result, we achieve this population exchange that gives us the conditional phase. We might start with quasi-static coupler population, and assuming some Maxwell-Boltzmannian statistics, we might draw this kind of diagram that helps us a bit with design considerations and helps us to understand the importance of hardware solutions to bring us to a low thermal, to low temperatures. So what we have here is that the Maxwell-Boltzmann statistics basically link temperature and frequency to thermal population. And here we demonstrate we achieve very low thermal population and low temperature in the order of 30 millikelvin in this frequency configuration where readout resonator is at around 6 gigahertz, qubit at 4 plus gigahertz, and coupler, let's say 1 gigahertz below. One important aspect of this research is leakage. And even though we have a tiny leakage, it does accumulate, and that is something we need to solve. Starting with single qubit RB, we can do RB and measure a coupler population. And we might observe that at the very minimal leakage, we still gain some population that is higher in steady state. Okay, these are very low numbers. That is due to good engineering. For 2-qubit gate, the leakage values are slightly higher, quite small still, but if you run thousands of 2-qubit Cliffords, what you will see is that you will achieve some steady state population that depends also on your coupler T1. And now the next question is that how important is this? Before that, I might highlight that for NISQ applications, which is basically few hundreds of 2-qubit Cliffords, the initial population is what matters, while in continuous operation, we need to start caring about the steady state population. Going into single qubit gates and the impact of coupler excitation in there, it can be understood intuitively by a frequency shift on the qubits that is due to a coupler excitation. So here we have a measurement of measurement data for 2 qubits here that reach a few megahertz dispersive shift. And in more general, it depends on the qubit coupler detuning and the coupling coefficients. And now you would have a mapping from this dispersive shift into single qubit gate error. And this can be understood as a kind of a miscalibration of your pulse due to this detuning. And then there's a model that nicely explains this. That depends on gate duration and this dispersive shift. I might want to highlight that this would be well correctable if we always deterministically knew the coupler state beforehand. And this will cause some added gate fidelity that on average scales with the population. So how does this work with 2-qubit gates? So I remind of what I showed before. But now when we add coupler excitation, we're in a manifold of one excitation higher. So now we also have more levels there. And in particular, we find this 030 state that interferes with the dynamics. So using the same calibration values for the CZ gate when the coupler was in the ground state, in the excited state case, we have a major leakage. So the population does not fully return here. And additionally to that, we have due to ZZZ, we have a conditional phase from the coupler excitation. We might want to experimentally look at it. So here, using IRB and starting from a reference case, we achieved quite nice CZ fidelity of 99.8% and Clifford fidelity of 99.3% for this experiment when the coupler is prepared in the ground state. But once we prepare the coupler into excited state, the performance drops dramatically to 76% Clifford fidelity. And we might be curious to see how it works in a superposition state. And this is still intuitive at this point. So it's a superposition of these two channels, basically. But interestingly, if we now extract with a fit the Clifford fidelity, it suggests us a very high fidelity of 99%, which is not in agreement of what we understand here. So I might want to highlight that the RB fit here doesn't capture the small coupler population and its impact on 2-qubit gates. That said, this type of error, coupler excitation, does have temporal and spatial correlations in your algorithm, so it's a really important topic. So we propose a solution that is coupler reset. And how to benchmark it is here that we repeat IRB segments here 40 2-qubit Cliffords long, and we interleave those with readout and reset gates, and then we observe the following for the reference case, and applying the coupler reset, we're able to mitigate the steady state population by factor 3. Here we use as a proof of concept a conditional reset on the coupler. I might summarize that here we demonstrated buildup of coupler population over repeated gates, the different mechanisms how coupler population impacts single and 2-qubit gates. We experimentally show that IRB doesn't capture the error contribution from initial coupler population, and the concept of applying interleaved coupler reset gates in the context of continuous algorithm to mitigate coupler population. Thank you.
Thanks, Alpo, for explaining us that thermal population really matters in most of the times. Please, questions. Here.
I'm not sure if you mentioned this, but so the coupler population contributes to 1-qubit and 2-qubit gate errors, but what's the numbers, like contribution numbers, like for like you mentioned like 99.94. So what's the contribution for such a fidelity?
So if you claim, let's say, 3.9 level CZ fidelity, you need to demonstrate low coupler population, because, as I showed, if the coupler is excited, the CZ gate performance is really low. For example, from the fact that you see that the 2-qubit Clifford is at 76% fidelity. So now, if you had 1% of coupler population, then you cannot have 3.9 gate. You can run the numbers. It might depend a bit on the architecture, but one rule of thumb is just like things won't work if you have coupler population. So the population would directly translate to 2-qubit gate error.
Okay.
Thank you for the question.
Yeah. Further question? Maybe I would have also one. So is there a chance actually by designing some robust pulses that you can get rid of this effect? Or is there some parameter regime where this might work out?
Yeah, that's a very good question. So for single qubit gates, you could, let's start from there, and there you could imagine, let's say, you try to, drive at 2 different frequencies. So independent of where the qubit was, you get the gate calibrated. That comes as a cost in fidelity, because then you need a longer gate. So there are trade-offs. So either you focus on not getting coupler population, or you do these resilient gates.
Yeah, so there might be a sweet spot in between. Okay,
Yeah.
there was one more question over there. Oh, sorry.
How do you do the coupler reset?
So here we use the proof of concept, just the active reset, which means that we read out the coupler state, and based on the readout, we either flip the state or not. So if coupler was excited, we apply a gate to bring it to ground state. Exactly, yeah, in this case, yeah.
Okay, let's thank Alpo again. And move on to our next talk, which will be given by Shinichi Ino. And it will be about parametrically driven iSwap gate using a capacitively shunted double transmon coupler at zero flux bias. So please, looking forward to the talk. Take it from there.
Okay, good afternoon, everyone. I'm Shinichi Inoue from Riken Institute and the University of Tokyo. So in this talk, I would like to talk about our recent paper on 2-qubit gate using a tunable coupler. So let me start with my device. So device is made of two fixed frequency transmons coupled through this tunable coupler, or the capacitively shunted double transmon coupler. So this is the same device as the one that we demonstrated the baseband CZ gate last year, and it appears in PL Applied in 2025. So one of the features of this gate is that this coupler is that there is a wide range of ZZ suppression from 0.2 to plus 0.2 flux quantum. So the next question is, or next direction is, how can we design an 2-qubit gate that actively leverages this wide range of ZZ suppression? Okay, so before talking about our 2-qubit gate, here's a quick review of the 2-qubit gates using frequency tunable elements. Broadly speaking, there are two kinds of control waveforms. One is the baseband DC, and another is a AC flux modulation. So the baseband flux gates, they can implement fast and high fidelity 2-qubit gates, but it is susceptible to the flux pulse distortions, and it requires careful pre-distortion calibration. And in addition, because the qubit and couplers are strongly hybridized during the gate operation, the system effective coherence time is degraded during this gate operation. So an alternative approach is parametric gate, that we apply parametric modulation to the coupler. And this approach is more robust against the flux pulse distortion, but widely studied, this first harmonic parametric gates requires the coupler to bias away from the zero flux sweet spot. So there is a flux sensitivity and the dephasing rate is increased. So another AC flux modulation approach is our 2-qubit gate, is a second harmonic parametric gate. Because the second harmonic generation is strongest at this zero flux sweet spot, the system naturally stays at this zero flux sweet spot, and it's not affected by the 1 over F noise. Yeah. Okay, and here is a core principle of the second harmonic generation. And if you take a look at this frequency response of the coupler, tunable coupler mode. So if you drive the coupler with the frequency of omega d, and because of the nonlinear response of the coupler, it will generate the second harmonic frequency. And as you can see from this expression, around this zero flux sweet spot, the first order component vanishes, and the system is not affected by the 1 over F noise. Oh, okay. Yes, so the next is how do we implement this iSwap interaction using the principle of second harmonic generation? The mechanism is actually simple, that if you drive the system at half the qubit detuning, in our case it's 249 megahertz, the system makes a second harmonic and there is an iSwap interaction between the data qubits. And interaction strength actually scales the square of the drive amplitude. And we have measured this chevron pattern on the left figure, and the center frequency is actually 245 megahertz, slightly below 249 because of the AC Zeeman shift. And we also measure this ISOP interaction strength as a function of the drive amplitude. At the weaker drive amplitude, it scales quadratically, but at stronger drives, it scales faster than quadratic because of the higher order terms. Okay, so the next is a gate tune-up. Because ISOP gate is a phase-sensitive gate, we need to correct some of the phases using the virtual Z gates. And in our implementation, this ISOP gate is made of 1 flux modulation plus 3 virtual Z gates. And yes, virtual 3 gates to compensate for the phase accumulation during the 2-qubit gate. And we use this tangent hyperbolic waveform to minimize the state leakage following the paper by our colleague. And the tune-up sequence is roughly in 3 steps. First, we tune up this ISOP amplitude and frequency to make this ISOP angle exactly 90 degrees. And after that, we we tune up the phases to make the ISOP the correct phases. And finally, we perform a joint optimization of the parameters using Orbit. It's a kind of randomized benchmarking-based optimization. Okay, so after tuning up the gate, we characterize the gate at various gate durations. At gate duration of 96 to 320 nanoseconds. At each gate duration, we recalibrated the parameters and evaluated the gate performance using a randomized benchmarking, and also we measure this ZZ-induced errors using echoed ISOP sequence. And you can see in this figure that most of the error is coming from the decoherence-induced errors, and the leakage is on the order of 0.01%, and the ZZ-induced error is actually surprisingly small until 100 nanoseconds. And below this point, the ZZ interaction-induced error starts to blow up, which ultimately limits the gate fidelity at shorter gate length. Okay, after sweeping the gate duration, we obtain the best ISOP fidelity of 99.92% at the gate duration of 112 nanoseconds. And in addition to this fidelity, the leakage is actually very small, and the population loss from the computational subspace is only around 5%, which is very small compared with other 2-qubit gates, where some of them loses like 20% at 20% outside the computational subspace. So in the later slides, I would like to explain 2 strengths why this ISOP gate is a high fidelity 2-qubit gate. Okay, so the first strength of our ISOP gate is a small hybridization with a coupler. Hybridization with a coupler will generally lead to the state leakage, and because the couplers are short-lived, hybridization with a coupler will decrease the effective coherence time of the system. So to quantify this hybridization, we numerically simulate the coupler hybridization at each flux bias point by taking the overlap between this bare state without any qubit couplings and the full dress states with all couplings enabled. So this plot shows that up until 0.3 flux quantum, the qubit and coupler hybridization is really small, but it starts to rapidly go up because the coupler frequency approaches the qubit ones. Okay. So as some of the audience might know, we have already demonstrated the baseband CZ gate with the same device. To make a comparison with the baseband CZ with our ISOP gate, we compared the control waveforms and the resulting qubit and coupler hybridization. Because the maximum flux excursion of the baseband CZ gate goes as high as 0.4 flux quantum, and our ISOP gate goes up to 0.28 flux quantum, the resulting the qubit and coupler hybridization is quite different. It is about 40% for the baseband CZ gate, and it's only 5% for the ISOP gate. So we believe that this small qubit and coupler hybridization is one of the key factors that enabled high fidelity ISOP gates even with a longer gate duration than 18 nanoseconds in the baseband CZ gate. Okay, so the second strength is a ZZ cancellation. Under the Frax modulation, this system experiences effective ZZ term that is described by two components. One is a negative average ZZ interaction that you can obtain by sampling this static ZZ interaction along the Frax trajectory. And under the Frax modulation, there is an additional term of dynamical ZZ interaction, which originates from the drive-induced level repulsion of the 1-1 state between 2-0 and 0-2 states. And if the qubits are designed in a far detuned regime, rather than their unharmonicities, this dynamical ZZ interaction becomes positive. So the negative average ZZ interaction and dynamical ZZ interaction can partially cancel each other, and it gives as small as minus 4.7 kilohertz at the modulation amplitude of 0.26. This is actually smaller than the minus 35.4 kilohertz during the idling. Okay, so finally, let me briefly explain the origin of the positive dynamical ZZ. This averaged static ZZ is understood in the laboratory frame, and this frequency-independent coupler-mediated coupling between the data qubits pushes the 1-1 state upward, and 2-0 state and 1-1 state pushes upward, and 1-1 to 0-2 pushes it downward. Because of the downward push is harder, this net average static ZZ is actually negative. And dynamical ZZ is well understood in the rotating frame of each qubit frequency. So in this frame, 1-0 state and 0-1 states are degenerate, and there is an ISOP interaction connecting these two states. Actually, this ISOP interaction opens a coupling path between 1-1 state and 2-0 and 0-2 states. Because 2-0 and 0-2 states are lower in energy than 1-0 and 0-2, 1-1 state is pushed upwards, which makes positive ZZ interaction, and these two partially cancel with each other. Okay, so to summarize, we demonstrated a high fidelity ISOP gate using a capacitively shunted DTC and by applying a parametric drive to the coupler. And this 2-qubit gate realizes 99.92% fidelity with a total gate duration of 112 nanoseconds, which benefits from the small qubit coupler hybridization and partial ZZ cancellation. Yes, thank you very much for your attention. I'm happy to take the questions.
Thanks. So thanks a lot for demonstrating that also with parametric gates we can get high gate fidelities in rather short times. Questions? There is one over there, Chris.
Let's talk. How does the presence of this sum mode that you have in the double transmon coupler play into the gate limited fidelity? Do you see any leakage into the sum mode, or is it just purely in the differential mode that you actually see the any kind of leakage in there? Have you analyzed this?
Do you mean another mode of the double transmon coupler?
The P mode.
P mode.
Yeah, how does that play into the limits of the fidelity of the gate?
Actually, this leakage randomized benchmarking measured all of the population leakage outside the qubit F states, and also as well as the M mode leakage and P mode leakage. And all combined, the population loss is only 5%. So I think it's quite small.
Is there a further question? If not, maybe a quick one. So what is the T1 time of the coupler, and how much does this limit?
T1 of the coupler is actually 100 microseconds for the tunable mode, okay, and 38 microseconds for the P mode, higher frequency mode. And they are limited by the flux line. And yes, these 2-qubit gate errors, all of them are higher than the coherence limits, and there is some gap between them.
Okay.
Yes.
Okay, thanks a lot. So thanks again for the very nice presentation. And with that, I would like to welcome Johannes Schirk on the stage, presenting us now a slightly different qubit, a fluxonium qubit, and talk about multifluxonium entanglement mediated by lumped element resonator couplers. Please, Johannes, take it from there.
Yeah, thanks. Hello, everyone. I'm very happy to be here to tell everyone about our recent advances in fluxonium processor architectures that we have been having at the WMI. So to motivate a bit, we already heard yesterday in Andreas' talk that for quantum error correction, we need to have high connectivity lattices, in particular for the surface code, we need square lattice architecture. And we also heard yesterday that this is something that in transmon architectures, this is already an established connectivity. However, if we look into fluxonium qubits, we're a bit behind on that. So so far, the demonstrated connectivities are trivial, or not trivial, but small scale devices with 2 qubits and a single coupler, or most recently, a linear chain of qubits. So this is where our work comes in. We are trying to establish this connectivity for unit cell. And the challenge for this, particularly with fluxonium qubits, is that the capacitance of the qubit is quite small, and still we want to achieve all of the things that people already in this session talked about, namely low ZZ interactions when while idling the qubits, having high fidelities on single and 2 qubit gates, and also having no spectator errors. And yeah, before I will tell you how we achieve this, I want to first motivate why we're excited about fluxoniums in the first place. So the qubit is built up from a single Josephson junction and an inductor, a shunt inductor. Those two together form a squid loop. And this squid loop, if you bias it to 0.5 flux, it creates this double well potential. And this double well potential creates a very unharmonic energy spectrum, in particular, the qubit frequency, so the 0-1 transition is very small, and the transition to higher excited states is very large. So, and that enables, first and foremost, the high single qubit gate fidelities, and also by exploiting these transitions to the higher excited states, we can get good controlled coupling to facilitate 2 qubit gates. And our approach now is to achieve this coupling with resonators, in particular with grounded resonators. So you can see here a circuit of the device, or a simplified circuit diagram. We have 2 fluxonium qubits here colored in yellow, and a coupler that is colored in green. And these are capacitively coupled together. So this creates this coupling scheme that is shown below. Basically, we have then 2 coupling pathways, one that is the direct qubit-qubit coupling, and another that is a qubit or an effective coupling mediated through the coupler. And by tuning our circuit parameters carefully, we can achieve we can balance these couplings such that they cancel the ZZ interaction, or not cancel it directly, but rather suppress it to well below a kilohertz. And the gate scheme that we're using is actually also borrowed from transmon qubits, and it's a resonator-induced phase gate. And the reason why this is interesting for fluxonium qubits is because we can use these aforementioned higher excited states, or the transitions out of the computational subspace, to couple to our resonator and create a dispersive shift. So as I show here in this energy diagram, we are placing the resonator frequency between the qubits 1-2 and 0-3 transition. And when we now introduce the coupling, this creates, or now on first on 1 qubit, this creates a dispersive shift. So if the qubit is in the 1 state, the resonator couples to the 1-2 transition. and gets shifted upwards. And if the qubit is in the 0 state, the resonator couples to the 0-3 transition and gets shifted downwards. Now, if we add the second qubit into the picture, we get in total 4 spectral lines. So this gives us the specificity for the computational states. And by now driving the resonator off resonantly, we can make a phase excursion, and so the qubit states accumulate a conditional phase. So far for the theory. So now I go to the implementation of the device. This is how it looks like. So we are implementing the connectivity for a unit cell with 5 fluxonium qubits, here again shown in yellow, and with 4 couplers. And the crucial step that makes this work for fluxonium qubits is the fact that these couplers are high impedance. And we implement this high impedance by having a lumped element resonator and 2 micrometer niobium wire, such that we can reach impedances of 150 ohms. And this step allows us to reach sufficiently small capacitive couplings to the fluxonium qubits to have 4 couplers on the same qubit. Here are is a summary of the device parameters. I'm not going to go into all of the details here, but the things of note is that we have this strong separation between the computational subspace and the interaction for the 2-qubit gate. And we have a very small static ZZ that we measure far below a kilohertz. And we also get high fidelity single qubit gates of 99.5%. And to this, I want to add that these qubits are also crosstalk free because of the low frequency of the fluxonium qubits. So the additional thing that we now need to have a working architecture is 2-qubit gates. And these we implement with 100 nanosecond pulses on our resonator. And here I'm showing an interleaved randomized benchmarking where you can see we reach a fidelity of 99.6% or almost 99.7%. But probably since I'm already highlighting a 3rd qubit here in this picture, you can see that there's something going wrong. I mentioned in the beginning that we want to avoid spectator errors. Well, in our architecture, we actually sometimes find that we do have them. So you can see that the fidelity of the randomized benchmarking is different if a spectator qubit, so the one that is not participating in the gate, is either in 0 or a 1. So we have an effective additional ZZ type interaction that is spurious. Luckily, this is something that we can actually correct for. I think there was also a question before here if you can deal with this using dynamical decoupling. And yes, you can. So the way you get rid of these errors is you split the resonator-induced phase pulse into 2 parts. And you then apply an echo pulse on the spectator qubit. And then in the first time slot, basically, you get a certain phase accumulation, and by flipping this qubit, the phase accumulation inverts, and then this effectively cancels the spectator error. So then, since the gate is a bit longer, we then effectively have a little bit lower fidelity, but still reach some 99.2% in this particular example. And below you can see the fidelities that we reach on the device. So finally, to prove that this is actually a working unit cell, we entangle all of the 5 qubits together by preparing the center qubit in an equal superposition state and applying CNOTs to all the qubits around, and then measuring the resulting state using quantum state tomography. And these are the fidelities that we get. So in order, this is for 3, 4, and 5 entangled qubits. We get 96.9%, 95.4%, and 90% of state fidelity for the entangled unit cell. So with that, I want to briefly summarize. So we, with this architecture, we implemented the first connectivity for fluxonium processor with low ZZ interaction with high single and 2 qubit gate fidelities, and we've shown that we can correct for spectator errors if we find them, and we entangled the entire processor also with high fidelity. And before I open the board for questions, I want to acknowledge that all of this work is only possible with a lot of people. So I highlighted here the Fluxonium team of the Walter Meissner Institute, and I also want to draw your attention to the final posters that we have from our institute. Thank you.
So thanks, Johannes, for showing us that also Fluxoniums lead to nice gates and nice architectures. Questions, please?
So you mentioned the errors are from the spectator qubit. So is there any way to control the resonator to turn off the coupling between the two qubits?
So actually, the error is caused not really by the coupling between the qubits, but it's caused between coupling of the couplers, right? So in our experiment, these are quite close in frequency, and this is what mediates actually the interaction. So an easy way to combat this in the future is really to just increase the detuning between the couplers themselves, and then you would reduce this error.
I see.
Thank you for the question.
Is there any further question? Yep, Janos.
Of the spectator qubit by using a NOT gate on it, right?
Yeah.
But what if the spectator qubit is in an X eigenstate?
So the effective operation on the spectator qubit is it really doesn't matter in which direction you apply the echo. It's just about that you invert kind of the action.
But if it is in an X eigenstate, then you are not doing anything to it with your gate, right?
Yes and no. You're changing the phase accumulation of the resonator by doing this. That's what's happening. So you're not. It's not the operation on the qubit that matters, but the kind of phase accumulation of the resonator.
Okay, thanks.
Maybe. Yeah. Okay.
Okay, I don't see any further questions. So thanks, Johannes, again for the presentation. And with that, we are coming to the last talk of this session, which is given by Anton Friskokum, who will tell us about fast parametric 2-qubit gates for fixed frequency qubits and tunable couplers. Please, Anton, stage is yours.
Thank you, Stefan. So in this session, we've heard a lot about both adiabatic gates and parametric gates. And perhaps you've been noticing that despite the name, the adiabatic gates have seemed to be quite a lot faster. So in this talk, I want to show you that perhaps this doesn't always have to be the case. Perhaps we can get faster with the parametric gates as well. So the outline for the talk is as follows. I will give some brief introduction to the parametric gates. Then we will see sort of the addition we make here to make them faster. We will make use of the intermediate states in the coupler. So we need to look at the 3-level system model to understand how this works. And then I'll show you some results, theory results for ISOP, but also some first experimental results from the experimental team here at Chalmers. And I want to say this is really work that's been driven by Dr. Jorge Fernandez Pendas, who was supposed to give this talk, but he's on parental leave, so I'm standing in for him today. So the setup we're considering and that we're using in experiments and in the quantum computers we're building here at Chalmers is fixed frequency qubits with a tunable coupler in between them. And in this setup, we can modulate the frequency of the tunable coupler by modulating the flux through the squid. And in this way, we get access to several parametric gates. So depending on the modulation frequency, we can choose sort of which transition we activate. We can activate the 0 to 01 transition to do an ISOP gate, or the 11 to 02 transition to do a CZ gate, for example. That was the wrong button. All right, so at Chalmers, as I said, we're doing these gates. Our 2-qubit gates have not been that fast so far. I mean, this is a few years old, this result I'm showing here. We're mostly coherence limited. There have been, in other groups, faster parametric gates done. They have gotten down under 100 nanoseconds and quite high fidelities, but we think we can go even further. So why do we want to go further? Well, we know I said that the gates we had here at Chalmers, they're mostly coherence limited. And we know from analytical work here at Chalmers and in other groups that the fidelity of our operation will depend on the gate time. It will decline linearly with the gate time, basically, and also with the coherence rates. So, of course, we want longer coherence times. And having fixed frequency qubits should help with that. That's why we have only tunable couplers. And then we also note that these most parametric gates, they don't use these intermediate states of the coupler. They only virtually excite the coupler, so the coupler decoherence doesn't come in. Now, if we're going to make use of the coupler, we might need to worry about this. That's a caveat for what I'm presenting today. So the 2-qubit gates can get faster. And we've seen from parametric gates that just driving harder or coupling strong doesn't really seem to help with this. You run into other problems. So we want to use, as I said, the coupler states to speed this up. And then we need to consider a 3-level system. Basically, we have some state in one with some excitation in 1 qubit perhaps, and then some intermediate state there with the coupler excited, and then a state involving the other qubit. And if you look at this, we will need to do full population transfer between the states that involve the qubits that are in the computational subspace. So we don't want to leave any population in the coupler, no leakage. And from this condition, you can derive now analytically some conditions on sort of the parameters in this setup. In this 3-level system, you need to be on resonance. You need to do this, have this interaction on for a certain time. And if you want to do a full cycle, so for a CZ gate, for example, you go from 1, to 2, 0 and back. You get some conditions there. If you want to do half a cycle, so going from one state to the other, like in the ISWAP from 0, 1 to 1, 0, you get some other condition. So making use of this now, we can also look at the 0, 1, and 2 excitation subspaces of the system. We can isolate sort of these 3-level systems. For example, for the ISWAP, we have a 3-level system here. For the CZ, we get some other 3-level system. And of course, in the CZ case, you need to check the dynamics for other computational states, but these things work out well. And then we are using now the parametric drive to achieve these resonance conditions that I was talking about that we saw on the previous slide. And you might need to use some more advanced drive here to cancel some unwanted components, but that's a sort of second-order problem. Okay, so now applying this to the ISWAP, we can take some typical parameters and typical couplings, typical frequencies and harmonicities and so on. And then we can scan sort of in coupler frequency. So we have the qubits fixed there, you see, close to the middle on the x-axis. And then you can scan the coupler frequency, and on the y-axis you scan the coupler modulation amplitude. And you see, so the color shows the fidelity, and you see with the darker colors means higher fidelity gates. And you see with the dashed lines, is sort of with a simple 3-level model predicts that you should have good gates. And you see it fits pretty well, this simple 3-level model. Now you can choose one particular point and look and sort of tune up a gate there. We do this in theory here for one point. We find here a gate in about 50 nanoseconds or even less, where we have very high fidelity, for example. And then in experiments now, what is this? This was not how the slide looked that I sent last night. Yes, they have done experiments in a group at Chalmers. Unfortunately, the reference and all the acknowledgement of people is hidden behind this humongous table. But you can see the results here at least. So they found a point here where they have about 50 nanosecond gate. And they do randomized benchmarking on this, and they find, this is partly hidden now, but they found 98.8% fidelity in this first experiment. And we think this is basically explained by decoherence, by coherence limit. So you have T1 and T2s for the qubits, but you also need to here worry about the coupler T1 and T2. Okay, so to summarize, we propose here to speed up parametric gates by really making use of the coupler intermediate state. And we've derived conditions for where you can find high fidelity gates and that are very fast. I showed you some example with around 50 nanoseconds, but you can get even faster than that. And I showed you some theory and experiment particular examples where you find good parameters. I did the examples for ISWAP, but as I said, the CZ works just in the same way, it just transitions between different other states. So this paper should be out during the fall as a preprint. I think some of you may remember me talking about this before and saying the paper should be out soon, but now it really, this time, it's on my desk for final edits. So I think this time we shouldn't have to wait too long. Yeah, let me thank the funding agencies and everyone involved, and I'm happy to take questions.
Thanks, Anton. So now we have learned that also with parametric gate, we can be fast and then soon also at highest fidelity. Stage is as always open for discussions and questions. Here's one.
Thank you for a nice talk. In your previous slide, there was chevron pattern, and the second chevron was asymmetric in the frequency. What do you think is happening?
I don't know. I hadn't contemplated that further. I think the Emil, are you here? The PhD student doing the experiment?
Yeah, this shape is to be expected. I don't remember why right now, but I think forward your question to Simon, who is also involved.
Refer it further. Further questions? People are getting tired a bit. It's soon over. One more question. Maybe then I have one. So do you know how hard is it to calibrate and tune the gate up? Because now you have two drives and you probably have to worry about stark shifts, that you're shifting the levels around with tuning amplitudes of two tones.
You still have one drive.
So I thought it's two legs that you have to
Yeah, no, that's
populate.
it's the coupling activated by the same drive. It's
but you have two tones, right?
No, you have one tone.
Maybe then. Okay.
We can talk more later.
Then we talk about this later. Okay. So with that, let's thank Anton again, and let's thank all of the speakers of this session. And there will be now some announcement by Lisa about how we continue here with the conference and the excursions. Thanks.
Yes, and thank you to Stefan for sharing the session.
All right, everybody. If you're feeling a bit low on energy, not to worry. We have some wraps and drinks for you downstairs, and then an evening of excursions, two of which you had to sign up onto in advance. If you signed up for Chalmers tour or scaling tour and you have not received a confirmation email, I am sorry, you're stuck on the wait list. What we do have to offer instead is a walking city tour that will also start right in front of this building, or just enjoy this beautiful evening for that matter. Those of you that got spots to these tours, please meet outside the spinning gates that you entered in this morning. There will be people with signs to help you locate the right spot. All right, with that, thank you for our first full day of SQA. Enjoy.